Imagine standing at the edge of everything you've ever known. Behind you, 100 billion stars blaze in the spiral arms of a galaxy not unlike our own. Planets orbit those stars. On some of them, perhaps, life has taken root. Civilizations may have risen and fallen across millions of years. All of it contained within this single cosmic island floating in the dark. Now turn around. Look outward, past the last scattered stars, past the faint halo of ancient suns that barely cling to the galaxy's gravitational embrace. Look into the space between. What do you see? At first glance, nothing. A void so complete, so utterly empty, that light itself seems to hesitate before crossing it. A darkness that stretches not for thousands of miles, not for millions, but for millions of light years. Distances so vast that if you traveled at the speed of light, the fastest anything can move in our universe, you would still be journeying for eons before reaching the next galactic shore. For most of human history, we assumed this space between galaxies was exactly what it appeared to be. Empty, vacant, a cosmic wasteland separating the bright islands of matter and energy. We were wrong. Profoundly, magnificently, almost unbelievably wrong. What exists between galaxies isn't nothing. It's everything. More matter than all the stars and all the galaxies combined. Structures so immense, they make galaxies look like grains of sand on an infinite beach. Filaments of hot gas stretching across the entire observable universe like a cosmic web spun by some unimaginable spider. And perhaps most disturbing of all, something is out there that we cannot see, cannot touch, cannot detect through any instrument we've ever built. Something that outweighs all visible matter by a factor of 5 to 1. Something that shaped the very universe we inhabit. Tonight, we journey into the darkness between the light. We explore the space between galaxies. And what we find there will change everything you thought you knew about the cosmos. Welcome back to the channel. I'm so glad you've joined me for what I think is going to be one of our most fascinating explorations yet. If you're new here, this is where we dive deep into the greatest mysteries of the universe. We don't just skim the surface, we plunge into the depths. We examine the evidence, we explore the theories, and we grapple with questions that have puzzled humanity's greatest minds for generations. And tonight's question is deceptively simple. What exists in the vast empty spaces between galaxies? You might think you know the answer. You might assume it's just empty space, a vacuum, with perhaps a few stray atoms floating around. But as we'll discover over the next 2 hours, intergalactic space is one of the most mysterious, most complex, and most important regions of the cosmos. Here's what we're going to explore together. First, we'll journey back to the early 20th century, when astronomers were just beginning to understand that the Milky Way wasn't alone in the universe. We'll see how our understanding of intergalactic space evolved from complete mystery to partial comprehension, and why so much still remains unknown. Then we'll dive into the physics of what should exist between galaxies. We'll explore the intergalactic medium, a term for the tenuous gas and matter that permeates the cosmic voids. We'll learn why this material, despite being incredibly sparse, actually contains more matter than all the galaxies combined. We'll investigate the cosmic web, the largest structure in the known universe, and see how galaxies are connected by filaments of matter stretching across billions of light years. We'll learn about the superclusters, the voids, and the strange walls of galaxies that define the architecture of the cosmos. And then things will get really interesting. We'll confront dark matter, the invisible scaffolding that holds the universe together. We'll explore why scientists believe something we cannot see makes up most of the matter in existence. We'll examine the evidence, the theories, and the ongoing search to finally detect this cosmic phantom. We'll discuss intergalactic stars' lonely suns that wander the void between galaxies, expelled from their homes and drifting through darkness for billions of years. We'll discover that there may be more stars between galaxies than within them. We'll explore the possibility of life in intergalactic space. Could something survive out there? Could something even thrive? And finally, we'll confront the ultimate fate of the intergalactic medium and what it tells us about the eventual end of the universe itself. This is a journey that spans scales almost impossible to comprehend. We'll zoom from individual atoms to structures spanning billions of light years. We'll travel back to the first moments after the Big Bang and forward to a future so distant that all the stars have long since burned out. So settle in. This is the perfect video to watch while pondering the deeper mysteries of existence. Whether you're here to learn, to wonder, or simply to let your mind drift across the cosmos, I promise you this: by the end, you'll never look at the night sky the same way again. Let's begin. For most of human history, we had no idea there was anything beyond our own galaxy. Think about that for a moment. For thousands of years, every philosopher, every astronomer, every curious person who looked up at the night sky believed they were seeing the entire universe. The band of light we call the Milky Way seemed to encompass everything that existed. Our cosmic address was simple. We lived in the universe, and the universe was the Milky Way. Oh, there were hints that something else might be out there. As far back as the 10th century, Persian astronomer Abi al-Rahman al-Sufi observed what he called a little cloud in the constellation of Andromeda. This fuzzy patch of light would later prove to be the nearest large galaxy to our own. But al-Sufi had no way of knowing that. To him, it was simply an interesting celestial curiosity. For centuries, these nebulae, from the Latin word for clouds, remained mysterious objects. Some astronomers thought they were clouds of glowing gas within our own galaxy. Others suspected they might be distant island universes, separate systems of stars incredibly far away. But without the technology to resolve them into individual stars, there was no way to know for certain. The debate raged for over 100 years. On one side were astronomers who believed the Milky Way was the entire universe, with these nebulae being merely local phenomena. On the other side were those who suspected the cosmos was far, far larger than anyone imagined. The question was so contentious that on April 26, 1920, two of America's most prominent astronomers faced off in what became known as the Great Debate. Harlow Shapley argued that the Milky Way was the entire universe. He pointed out that our galaxy was enormous, far larger than previously believed, and that these spiral nebulae were likely just nearby objects within it. Heber Curtis disagreed. He believed the spiral nebulae were distant galaxies in their own right, separated from us by vast stretches of empty space. Neither man could prove his case definitively. The technology simply didn't exist, but that was about to change. Just 3 years later, in 1923, a young astronomer named Edwin Hubble was observing the Andromeda Nebula through the newly completed 100-inch Hooker telescope at Mount Wilson Observatory in California. It was the largest telescope in the world at the time, and Hubble was using it to study what he initially thought was a nova and exploding star in Andromeda. But as he examined his photographic plates more carefully, Hubble realized he wasn't looking at a nova at all. He was observing a Cepheid variable star, a type of star whose brightness pulses in a regular pattern. And here's why that mattered. Astronomers had discovered that Cepheid variables have a direct relationship between their pulsation period and their true brightness. If you know how bright a Cepheid truly is, and you measure how bright it appears from Earth, you can calculate exactly how far away it is. Hubble did the math, and the result was staggering. The Andromeda Nebula wasn't inside our galaxy at all. It was roughly 900,000 light-years away, far beyond the boundaries of the Milky Way. We now know that Hubble's measurement was actually an underestimate. Andromeda is about 2.5 million light-years distant. But the key finding stood. Andromeda was another galaxy entirely. The universe had just gotten unimaginably bigger. But here's the question that immediately followed. If Andromeda is a separate galaxy, and our Milky Way is a galaxy, what's in between them? For the first time in history, humans had to grapple with the concept of intergalactic space. Straightforward. Nothing. Absolutely nothing. The space between galaxies appeared to be a perfect vacuum, emptier than anything we could create on Earth, emptier than anything we had ever imagined. While the space between stars within a galaxy might contain a few atoms per cubic centimeter, the space between galaxies seemed to contain essentially zero, a void more complete than emptiness itself. This made intuitive sense. After all, galaxies were where all the matter was. Stars, planets, gas clouds, dust, everything that made up the visible universe seemed to be concentrated in these island-like structures. The space between them was simply space, empty, black, featureless. For several decades, astronomers largely accepted this view. Intergalactic space was interesting only in the sense that it separated interesting things. It was the cosmic equivalent of ocean between continents, important for defining distances, but essentially empty and uniform. But nature, as it so often does, had surprises in store. The first hints came in the 1960s, when astronomers began observing distant quasars, incredibly luminous objects that we now know are supermassive, black holes actively consuming matter at the centers of distant galaxies. Quasars are so bright that their light can travel across billions of light-years of space before reaching our telescopes. And here's where things got interesting. When astronomers analyzed the light from distant quasars, they noticed something odd. The light had been partially absorbed during its long journey to Earth. Specific wavelengths were missing, absorbed by clouds of hydrogen gas somewhere between the quasar and our telescopes. But these absorption features didn't match what you'd expect from gas within galaxies. The patterns suggested something else: vast clouds of hydrogen floating in the space between galaxies. Not just a few atoms here and there, but enormous structures of gas stretching across millions of light years. Intergalactic space, it seemed, wasn't empty at all. This discovery opened a floodgate of new questions. How much gas was out there? Where did it come from? How was it distributed? What role did it play in the evolution of galaxies and the universe itself? Over the following decades, astronomers would develop increasingly sophisticated techniques to study this intergalactic medium. They would discover structures far more complex and vast than anyone had imagined. And they would ultimately realize that the space between galaxies contains more mystery than the galaxies themselves. But before we dive into those discoveries, we need to understand something fundamental about the nature of intergalactic space itself. Let's talk about what it means for something to be empty. When we say intergalactic space is a vacuum, what do we actually mean? On Earth, when we create a vacuum chamber in a laboratory, we pump out as much air as possible. A really good vacuum might contain only a few million molecules per cubic centimeter. That sounds like a lot, but compared to the air you're breathing right now, which contains about 25 quintillion molecules per cubic centimeter, it's practically nothing. The space between stars within our galaxy is even emptier. In the interstellar medium, you might find just one atom per cubic centimeter. That's trillions of times emptier than the best vacuum we can create on Earth. Intergalactic space takes emptiness to an entirely different level. In the vast voids between galaxies, there might be only one atom per cubic meter. Sometimes even less one atom per 10 cubic meters, or per 100 cubic meters. We're talking about a level of emptiness that makes the space between stars look positively crowded. To put this in perspective, if you took a cubic kilometer of intergalactic space, a volume large enough to contain millions of Olympic swimming pools, you might find enough matter to make a single grain of sand, maybe. And yet, here's the mind-bending part. When you add up all that incredibly sparse matter across the unimaginably vast distances between galaxies, it amounts to more than all the matter in the galaxies themselves. Let me say that again, because it's one of the most counterintuitive facts in all of astronomy. There is more matter floating in the near-empty voids between galaxies than in all the stars, planets, and gas clouds within galaxies combined. How is this possible? The answer lies in scale. Yes, the density of matter in intergalactic space is incredibly low, but intergalactic space is incredibly vast. The distances between galaxies dwarf the galaxies themselves. If you could somehow compress all the matter in the Milky Way into a dense ball and place it in intergalactic space, it would be like dropping a grain of sand into the Pacific Ocean. The ocean contains far more water, despite being made of the same molecules as a glass of water, simply because there's so much more of it. This is the first great revelation about intergalactic space. It's not empty at all. It's sparse, certainly, diffused beyond anything we experience on Earth. But empty? Not even close. And this intergalactic gas, what astronomers call the intergalactic medium, or IGM, is far from simple or uniform. It contains structures, variations, and mysteries that we're still working to understand. But here's where things get really strange. Even when we account for all the gas in intergalactic space, even when we add up every hydrogen atom and helium nucleus and trace heavy element floating in the void, we still can't explain the universe we observe. Something else is out there. Something far more massive than all the visible matter combined. Something we cannot see, cannot touch, cannot detect with any instrument we've ever built. We call it dark matter, and it might be the most important thing in intergalactic space, despite the fact that we have no idea what it actually is. But we're getting ahead of ourselves. Before we explore dark matter, we need to understand something even more fundamental: the structure of the universe itself. Because intergalactic space isn't just a formless void. It has architecture. It has patterns. It has a skeleton of invisible matter that shapes everything we see. Coming up, we'll explore the cosmic web, the largest structure in existence. And what we find will reshape everything you think you know about the organization of the cosmos. Imagine you could step outside the universe. Not outside our galaxy, we've already done that conceptually. Not outside our local group of galaxies. I mean truly outside, viewing the entire observable universe from some impossible vantage point, like an astronomer looking at a specimen under a microscope. What would you see? For a long time, scientists assumed you'd see a fairly random distribution of galaxies. Sure, they knew galaxies clustered together in groups and clusters. The Milky Way is part of the local group, which includes Andromeda and about 50 smaller galaxies. That local group is part of the larger Virgo supercluster. But the overall arrangement, the big picture, was assumed to be more or less random. Galaxies scattered across space like stars across the night sky, patchy in places, but without any grand organizing principle. That assumption turned out to be spectacularly wrong. In the 1980s, astronomers began conducting systematic surveys of galaxy positions in 3 dimensions. Earlier surveys had mapped the sky in 2 dimensions, like taking a photograph. But to understand the true structure of the universe, you need depth. You need to know how far away each galaxy is. This is where spectroscopy comes in. By analyzing the light from distant galaxies, astronomers can measure their redshift, how much the light has been stretched by the expansion of the universe. The greater the redshift, the farther away the galaxy. Using this technique, researchers began building 3-dimensional maps of the cosmos for the first time. The results were shocking. In 1986, astronomers Margaret Geller and John Hoekra published the results of what they called the CFA Redshift Survey. They had mapped the positions of over 1,000 galaxies in a slice of the northern sky. And when they plotted those positions, what emerged looked nothing like random scatter. The galaxies formed vast chains and walls surrounding enormous empty regions. It looked less like scattered stars and more like bubbles, or foam, or perhaps most accurately, a sponge. The galaxies weren't randomly distributed. They traced out the surfaces of vast, empty voids. Geller and Hoekra had discovered what would become known as the Great Wall. a filament of galaxies stretching more than 500 million light-years across space. At the time, it was the largest known structure in the universe. It was also utterly unexpected, but this was just the beginning. As survey technology improved and astronomers mapped larger and larger volumes of space, the pattern became clearer and more intricate. Galaxies weren't just forming random chains. They were tracing out a cosmic web, a vast network of filaments connecting dense nodes, surrounding enormous voids. Picture a three-dimensional spider web, but on a scale almost impossible to comprehend. The strands of the web are made of galaxies, gas, and matter, stretching across millions and billions of light-years. Where multiple filaments meet, you find galaxy clusters, dense concentrations of hundreds or thousands of galaxies bound together by gravity. And between the filaments, filling most of the volume of the universe, are vast empty regions called cosmic voids. This is the cosmic web, and it's the fundamental architecture of the universe. Let me try to give you a sense of scale here, because scale matters. The local group, our little neighborhood of galaxies, is about 10 million light-years across. It contains two large spiral galaxies, the Milky Way and Andromeda, one medium-sized galaxy, Triangulum, and perhaps 50 or more smaller dwarf galaxies. The local group is part of the Virgo supercluster, which is about 110 million light-years across. It contains roughly 100 galaxy groups and clusters. The Virgo supercluster is part of an even larger structure called Laniakea, which was only identified in 2014. Laniakea is about 520 million light-years across and contains about 100,000 galaxies. And Laniakea is just one of many superclusters that form the filaments of the cosmic web. The largest filaments we've discovered stretch for billions of light-years. The Hercules corona Borealis Great Wall, identified in 2013, is roughly 10 billion light-years across, so large that light takes 10 billion years just to cross it. It's the largest known structure in the observable universe. Between these filaments are voids regions containing very few galaxies, and these voids are enormous. The Boat's void, one of the largest known, is roughly 330 million light-years in diameter. It contains only about 60 galaxies compared to the thousands you'd expect in a similar volume of average space. This is intergalactic space in its purest form, not the relatively crowded regions between nearby galaxies, but the vast empty expanses between filaments. These voids are as close to true emptiness as anywhere in the universe. But even here, in the darkest, emptiest regions of the cosmos, there is something. The matter in the cosmic web isn't just galaxies. In fact, the galaxies are just the most visible part. They're like lights on a Christmas tree, bright and obvious, but not the whole structure. The real substance of the cosmic web is invisible. Most of the regular matter, what physicists call baryonic matter, made of protons, neutrons, and electrons, exists as diffuse gas in the filaments. This is the warm-hot intergalactic medium, or WHIM, and it accounts for roughly half of all baryonic matter in the universe. For decades, astronomers called this missing matter not dark matter, which is something else entirely, but regular matter that we knew should exist but couldn't find. The Big Bang had produced a certain amount of hydrogen and helium. We could calculate exactly how much from the cosmic microwave background radiation, but when astronomers added up all the matter they could see, in stars, in galaxies, in gas clouds, it fell short. About half the baryonic matter seemed to be missing. The solution? It was hiding in the cosmic web. This gas is incredibly hot temperatures of hundreds of thousands to tens of millions of degrees. At these temperatures, hydrogen atoms are fully ionized, stripped of their electrons. This makes the gas very hard to detect. It doesn't emit much visible light, and the X-rays it produces are extremely faint. But starting in the early 2000s, astronomers began developing techniques to observe this elusive gas. They looked for absorption of light from distant quasars. They searched for faint X-ray emission. They used sophisticated computer simulations to predict where the gas should be, and then targeted those regions with telescopes. And gradually, the cosmic web revealed itself. In 2018, researchers finally made the first direct observations of filaments connecting galaxy clusters. Using extremely long exposures on the Very Large Telescope in Chile, they detected faint blue light coming from hydrogen gas stretched between clusters hundreds of millions of light years apart. The cosmic web was no longer just a theoretical prediction. It was directly observed. But here's what's really remarkable about this structure. We can explain why it exists. The cosmic web isn't random. It isn't a fluke. It's a direct consequence of how the universe began and how gravity works over cosmic timescales. To understand this, we need to go back to the very beginning. In the first fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion called inflation. During this time, quantum fluctuations, tiny random variations in density caused by the fundamental uncertainty of quantum mechanics, were stretched to cosmic scales. When inflation ended, these fluctuations were imprinted on the matter and energy of the universe. Some regions were slightly denser than average. Others were slightly less dense. The differences were incredibly tiny, just a few parts in 100,000, but they were enough. As the universe cooled and expanded, gravity began to do its work. Slightly denser regions attracted more matter. Slightly less dense regions lost matter to their denser neighbors. Over millions, then billions of years, these tiny initial differences grew into the vast structures we see today. The denser regions collapsed into galaxies and galaxy clusters. The less dense regions became the voids, and the boundaries between them, the surfaces of the growing voids, became the filaments of the cosmic web. This is called hierarchical structure formation, and it's one of the great triumphs of modern cosmology. Starting from simple initial conditions and the known laws of physics, we can simulate the formation of the cosmic web on computers. And the simulations match what we observe in the real universe. But there's a catch. When we run these simulations using only the visible matter, the gas and dust, and atoms we can detect, the web doesn't form properly. The structures are too weak. They don't match observations. Something is missing. To make the simulations work, To produce a cosmic web that looks like the real one, we need to add something else. Something that provides additional gravitational pull. Something that was there from the beginning, shaping the formation of structure at every scale. We need dark matter. And this brings us to one of the deepest mysteries of intergalactic space and of the universe itself. But before we dive into dark matter, let me pause here for a moment. Look at what we've discovered so far. We started with the assumption that intergalactic space was empty of void between the islands of galaxies. But we found that it contains vast structures of gas and matter. We found that the universe has a web-like architecture stretching across billions of light years. We found that most of the regular matter in the universe exists not in galaxies, but in the hot gas between them. And yet, this is just the beginning. Because all the matter we've discussed so far, the gas and filaments, the stars and galaxies, the atoms and planets, and people accounts for only about 5% of the universe. The rest is something else entirely. Coming up, we enter the realm of the invisible. We explore dark matter and dark energy, the twin mysteries that make up 95% of everything that exists. What are they? Where did they come from? And how do they shape the vast emptiness between galaxies? The answer, as we'll see, is stranger than you ever imagined. In 1933, a Swiss astronomer named Fritz Zwicky made a discovery that should have shaken physics to its core. Zwicky was studying the Coma Cluster, a massive collection of over 1,000 galaxies located about 320 million light-years from Earth. He was trying to measure the total mass of the cluster using two different methods. The first method was simple. Count up all the visible matter. Look at all the galaxies in the cluster. Estimate their masses based on their brightness. Add them together. Total visible mass. The second method was more subtle. It involved measuring how fast the galaxies were moving. You see, a galaxy cluster is held together by gravity. The galaxies orbit the cluster's center, much like planets orbit a star. And the speed of those orbits depends on the total mass. The more mass, the stronger the gravity, the faster the galaxies must move to maintain their orbits. Zwicky measured the velocities of galaxies in the Coma Cluster. He applied the mathematics, and he got a shocking result. The galaxies were moving far too fast. Based on their speeds, the cluster should have flown apart billions of years ago. There simply wasn't enough visible mass to hold it together. Yet there it was, clearly intact, a stable structure that had existed for cosmic ages. Zwicky's conclusion was radical. There must be invisible matter in the cluster. Matter that doesn't emit or reflect light, but still exerts gravitational force. He called it dunkel mattery dark matter. It was a brilliant deduction. It was also almost completely ignored. For 40 years, Zwicky's discovery languished in obscurity. Astronomers weren't ready to accept that the universe contained vast amounts of invisible matter. They assumed Zwicky had made an error, perhaps in his velocity measurements, or in his mass estimates, or in his mathematical analysis. But then, in the 1970s, the evidence became impossible to ignore. Vera Rubin, an American astronomer, was studying the rotation of spiral galaxies. She was measuring how fast different parts of each galaxy moved, the inner regions near the center, and the outer regions at the edge. According to conventional physics, the outer regions should move more slowly than the inner regions. This is how orbits work. Think about our solar system. Mercury, close to the Sun, orbits in just 88 days. Neptune, far from the Sun, takes 165 years. The farther from the center, the slower the orbit. Galaxies should work the same way. Most of the visible mass is concentrated near the center, in a dense bulge and inner disk. So stars in the outer reaches of a galaxy should orbit slowly, taking hundreds of millions of years to complete a single circuit. But that's not what Rubin found. Galaxy after galaxy, the pattern was the same. The outer regions rotated just as fast as the inner regions. In some cases, faster. The rotation curves were flat or even rising where they should have been falling. This was impossible. Unless there was more mass than we could see. Unless galaxies were embedded in vast halos of invisible matter, extending far beyond the visible stars and gas. Halos that contained far more mass than the galaxies themselves. Rubin had rediscovered Zwicky's dark matter, but this time the evidence was undeniable. It wasn't just one cluster, it was every galaxy she studied. The pattern was universal. Within a decade, the astronomical community had come to accept what Rubin and Zwicky had discovered. Dark matter was real. It existed throughout the universe, and there was a lot of it, roughly 5 times as much dark matter as ordinary matter. But what was it? This is where things get strange. Because despite almost a century of searching, despite hundreds of experiments and thousands of scientific papers, we still don't know what dark matter actually is. Let me be clear about what we do know. We know dark matter exists. The evidence is overwhelming. Galaxy rotation curves, the dynamics of galaxy clusters, the cosmic microwave background, the formation of large-scale structure, gravitational lensing, the bending of light by massive objects. Every line of evidence points to the same conclusion. The universe contains far more matter than we can see. We know roughly where dark matter is. Computer simulations show that it forms vast halos around galaxies, extending far beyond the visible stars. These halos are embedded in even larger structures that trace the cosmic web. Dark matter provides the gravitational scaffolding on which visible matter accumulates. We know how dark matter behaves. It doesn't interact with light. It doesn't emit, absorb, or reflect electromagnetic radiation. It doesn't interact with regular matter except through gravity. It doesn't collide with itself in the usual sense. It's effectively invisible and intangible, and we know how much of it there is. Dark matter makes up about 27% of the total energy content of the universe. Regular matter, the stuff we're made of, the stuff we can see and touch, makes up only about 5%. But we don't know what it is. For decades, the leading candidates were so-called WIMPs, weakly interacting massive particles. These hypothetical particles would have a small mass, a few to a few hundred times the mass of a massa proton, and would interact very weakly with regular matter. WIMPs were attractive because they naturally produced the right amount of dark matter in the early universe. a coincidence physicists called the WIMP miracle. Physicists built elaborate experiments to detect WIMPs. They placed detectors deep underground, shielded from cosmic rays and other interference. They waited for the rare occasion when a WIMP might bump into a nucleus of regular matter, producing a tiny detectable signal. They waited and waited and waited. No WIMPs. Experiment after experiment set ever tighter limits on WIMP properties. The allowed parameter space shrank. The WIMP miracle began to look less like a miracle and more like a mirage. Today, many physicists are exploring alternative candidates. Axions, extremely light particles, originally proposed to solve problems in quantum chromodynamics. Sterile neutrinos, hypothetical cousins of the known neutrinos that interact only through gravity. Primordial black holes, objects formed in the early universe that might account for some or all of dark matter. But here's the unsettling truth. We don't know. We've spent nearly a century studying something that makes up the majority of the matter in the universe, and we still have no idea what it actually is. This might seem like an academic puzzle, disconnected from the vast spaces between galaxies that we're exploring tonight. But it's not. Dark matter isn't just a curiosity. It's fundamental to understanding intergalactic space. Remember the cosmic web we discussed in the last chapter? The vast network of filaments connecting galaxies, surrounding empty voids? That web exists because of dark matter. Let me explain how. In the early universe, right after the Big Bang, matter was distributed almost, but not quite uniformly. There were tiny density fluctuations, regions slightly denser or less dense than average. These fluctuations existed in both regular matter and dark matter. But here's the key difference. Regular matter in the early universe was ionized. Electrons were stripped from atoms, creating a plasma of charged particles. This plasma interacted with light, which created pressure that resisted gravitational collapse. Regular matter couldn't clump together easily, not while the universe was still hot and radiation dominated. Dark matter had no such limitation. It doesn't interact with light, so there was no radiation pressure to resist its collapse. While regular matter was still coupled to radiation, dark matter began to gravitationally clump. It fell into the slightly denser regions, making them denser still. It flowed away from the less dense regions, making them emptier. By the time the universe cooled enough for regular matter to decouple from radiation, about 380,000 years after the Big Bang, dark matter had already formed web-like structure. Halos and filaments and voids were already in place, traced out in invisible matter, and then regular matter fell in. Released from radiation pressure, normal atoms flowed down the gravitational gradients created by dark matter. They accumulated in the dark matter halos. They formed the first stars and galaxies. They traced the filaments of the cosmic web because those filaments were made of dark matter. This is why I call dark matter invisible scaffolding. It's not just that dark. Matter exists alongside the visible universe. It's that dark matter created the framework on which the visible universe was built. When you look at a galaxy, you're seeing the luminous center of a vast dark matter halo. When you observe the cosmic web, you're seeing visible matter tracing invisible structures. When you map the distribution of galaxies across billions of light years, you're mapping the distribution of dark matter. And this has profound implications for intergalactic space. Because if dark matter shaped the cosmic web, then dark matter also shaped the voids. Those vast empty regions between galaxies aren't empty of dark matter, they're just less dense. Dark matter still exists there, just spread more thinly than in the filaments and halos. In fact, computer simulations suggest that even the emptiest voids contain small halos of dark matter. These halos might be too small to host galaxies. They lack the mass to accumulate enough gas for star formation. But they exist nonetheless. Billions and billions of them, scattered throughout the voids, invisible and undetectable. What would it be like to visit such a halo? Imagine drifting through the deepest void, millions of light years from the nearest galaxy. Around you, nothing visible, just the faint glow of distant galaxies on the cosmic horizon. No stars, no planets, no gas clouds thick enough to see. And yet, you would not be alone. Surrounding you, extending for thousands of light years in every direction, would be a halo of dark matter, invisible, intangible, passing through your body without the slightest interaction. But they're exerting its gravitational pull, shaping the motions of anything that wandered close. This is the true nature of intergalactic space. Not a void, but a subtle landscape of invisible matter. Not empty, but filled with something we cannot see or touch, something that makes up most of the universe. But dark matter, strange as it is, accounts for only 27% of the cosmos. What about the remaining 68%? This is where we encounter something even more mysterious. Something that doesn't just shape space, it defines its fate. It's called dark energy, and it's making intergalactic space grow larger every second. Let me explain. In the late 1990s, two teams of astronomers set out to measure the expansion rate of the universe. They were using Type Ia supernova stellar explosions that produce a predictable, standard amount of light as cosmic distance markers. By comparing how bright these supernovae appeared to how far away they should be based on their redshift, the astronomers could trace the history of cosmic expansion. Everyone expected the expansion to be slowing down. After all, gravity attracts. All the matter in the universe should be pulling on all the other matter, gradually decelerating the expansion that began with the Big Bang. The only question was how much deceleration. But that's not what the teams found. The expansion wasn't slowing down. It was speeding up. Distant supernovae were dimmer than expected farther away than they should be if the expansion were decelerating or even constant. The universe wasn't just expanding. It was accelerating. This was completely unexpected. Gravity should be slowing things down, not speeding them up. Something was pushing the universe apart, some form of energy that counteracted gravity on cosmic scales. We call this dark energy. And like dark matter, we have no idea what it is. What we know is that dark energy behaves like a property of space itself. The more space there is, the more dark energy there is. And as the universe expands, creating more space, there's more dark energy to push the expansion faster. Dark energy makes up about 68% of the universe. It's the dominant component of the cosmos, more significant than dark matter, far more significant than ordinary matter. And it's making intergalactic space grow. Every second, the distance between distant galaxies increases. Not because the galaxies are moving through space, but because space itself is expanding. New space is being created between galaxies, stretching the cosmic web, widening the voids. The rate of this expansion is measured by a quantity called the Hubble constant. For every megaparsec of distance, about 3.26 million, light-years galaxies recede from us at about 70 kilometers per second. That might not sound like much, but it adds up. For galaxies billions of light-years away, the recession velocity exceeds the speed of light. This sounds like it should be impossible. Nothing can move faster than light through space. But this isn't movement through space. It's the expansion of space itself, and there's no speed limit for that. This means that the observable universe has a horizon. There are galaxies so far away that their light will never reach a space is expanding faster than their light can travel toward us. These galaxies are beyond our cosmic horizon, and they're receding farther every day. For the regions of intergalactic space beyond this horizon, we will never know what exists there. We can't see it. We can't receive signals from it. We can't even know if it contains the same physics as our observable universe. And here's the truly sobering thought. That horizon is getting closer. As the expansion accelerates, more and more galaxies are being pushed beyond our reach. Today, about 94 billion light-years of space are theoretically accessible to us. But billions of years from now, distant galaxies will vanish over the cosmic horizon. The observable universe will shrink. Eventually, if current theories are correct, every galaxy beyond our local group will disappear. We'll be left alone in an ever-expanding void, with no evidence that the vast cosmic web ever existed. Dark energy is the ultimate architect of intergalactic space. It's stretching the voids. It's thinning the filaments. It's slowly, inexorably, pulling the universe apart. But we're getting ahead of ourselves. Before we explore the far future, we need to spend more time in the intergalactic present. Because despite everything we've discussed, the gas, the dark matter, the dark energy, we haven't yet talked about some of the strangest inhabitants of the cosmic void. Coming up, we meet the wanderers of intergalactic space. Stars without galaxies, planets without suns, objects that drift through the darkest emptiness. Their stories more mysterious than you can imagine. For most of the history of astronomy, the idea of a star existing outside a galaxy seemed almost nonsensical. Stars are born in the gas clouds of galaxies. They live their lives in the gravitational embrace of galactic structures. When they die, they seed their galaxies with heavy elements for the next generation of stars. A star outside a galaxy would be like a fish outside water, theoretically possible, perhaps, but deeply strange. And yet, they exist. In 1997, astronomers made a startling discovery while studying the Virgo cluster. They found light not from galaxies, but from between galaxies. Diffuse, faint, but unmistakable. When they analyzed this light, they realized it came from individual stars. Stars that weren't part of any galaxy. Stars floating freely in intergalactic space. We call them intergalactic stars or intracluster stars when they're found within galaxy clusters. And there are far more of them than anyone expected. Current estimates suggest that between 10 and 50% of all stars in a typical galaxy cluster exist between galaxies rather than within them. In the Virgo cluster alone, there may be 1 trillion intergalactic stars, 1 trillion suns wandering the void. How did they get there? The answer lies in the violent history of galaxy interactions. Galaxies don't exist in isolation. They're constantly pulling on each other, approaching each other, sometimes colliding with each other. When galaxies interact, the gravitational forces involved are staggering. Stars can be ripped from their home galaxies like leaves torn from trees in a hurricane. These ejected stars don't just disappear. They continue on trajectories that carry them into intergalactic space. Some might eventually be captured by other galaxies. Others might wander forever, never again calling any galaxy home. But violent ejection isn't the only mechanism. Sometimes the process is more gradual. When a smaller galaxy falls into a galaxy cluster, it's stripped of its outer stars and gas by the gravitational tides of the cluster. This is called tidal stripping, and it can remove most of a galaxy's mass over billions of years. The stripped material doesn't vanish. It joins the intracluster medium, adding to the population of intergalactic stars. And sometimes, stars are ejected not by external forces, but by events within their home galaxy. Hypervelocity stars are objects moving so fast, often exceeding 1,000 kilometers per second, that they can escape their galaxy entirely. These extreme speeds typically result from close encounters with the supermassive black holes at galactic centers. A binary star system wanders too close. One star is captured, the other is flung outward at incredible velocity. It becomes a cosmic cannonball, racing toward intergalactic space. The fastest known hypervelocity star, S5HVS1, is moving at about 1,700 kilometers per second relative to the Milky Way. At that speed, it will escape our galaxy in a few million years and drift into the void. Think about what this means for a moment. Somewhere out there, in the darkest emptiness between galaxies, there are stars, not a few trillions of them. They carry no companions. They host no planets. Or if they do, those planets are cold, dark worlds lit only by the faint glow of their parent star and the distant shimmer of galaxies millions of light years away. What would it be like to orbit such a star? Imagine a world circling an intergalactic sun. Your sky would be unlike anything we experience. There would be no constellations as we know them, no familiar patterns of nearby stars. Instead, your heavens would be dominated by galaxies, faint smudges of light, each containing hundreds of billions of stars, but appearing as mere fuzzy patches from your lonely vantage point. The nearest star to your world might be hundreds of light years away, or even thousands. In our solar neighborhood, stars are separated by an average of about 4 light years. Between galaxies, that average distance might be 1,000 times greater. The isolation would be almost absolute. And yet, even in this isolation, the universe would not be static. Your intergalactic sun would still burn through its nuclear fuel. It would still age, still evolve, still eventually die. If it were massive enough, it might explode as a supernova, briefly outshining all the galaxies in your sky before fading into a neutron star or black hole. If it were smaller, it might swell into a red giant, perhaps engulfing your world, before shrinking into a white dwarf that would cool for trillions of years. Life on such a world, if life could exist, would evolve under conditions utterly unlike those on Earth. No galaxy to provide a sense of cosmic community. No stellar nurseries forming new stars nearby. Just one sun, one world, and an infinite dark. But intergalactic stars are just the beginning of the Wanderer story, because we now know that planets too can exist between galaxies. In 2011, astronomers using gravitational microlensing, a technique that detects objects by the way they bend light from background, sources discovered what appeared to be a free-floating planet in our own galaxy. Not a planet orbiting a star, but a planet wandering alone through interstellar space. Since then, evidence has mounted that such rogue planets are incredibly common. Some estimates suggest there could be billions or even trillions of them in our galaxy, alone more rogue planets than stars. And if rogue planets can exist in galaxies, they can exist between galaxies too. When stars are ejected into intergalactic space, they might carry their planetary systems with them. Or planets might be ejected separately, flung into the void by the same gravitational interactions that can eject stars. Once in intergalactic space, these worlds would drift forever, too far from any star to be warmed by sunlight. Could life exist on such worlds? It seems impossible at first. Life as we know it requires energy, and sunlight is the primary energy source for Earth's biosphere. A planet wandering between galaxies would be colder than any world we've ever studied temperatures, just a few degrees above absolute zero. But there's another possibility. Larger planets might have significant internal heat. This heat could come from radioactive decay of elements in the planet's core, or from tidal forces if the planet retained large moons. Such internal heat could potentially keep subsurface oceans liquid for billions of years, even in the absence of a star. We know this is possible because we see it in our own solar system. Europa, a moon of Jupiter, has a subsurface ocean kept liquid by tidal heating. So does Enceladus, a moon of Saturn. These worlds are far from the sun, in regions cold enough to freeze most liquid solid, yet they harbor vast oceans of liquid water beneath their icy crusts. A rogue planet in intergalactic space might be similar. Its surface would be frozen solid, exposed to the near absolute zero temperatures of the void. But beneath that frozen crust, heated from below, an ocean might exist. And in that ocean, who knows what might evolve? This is speculation, of course. We have no evidence of life on intergalactic worlds. We can barely detect such worlds at all. But the possibility reminds us that the spaces between galaxies, as empty as they appear, might contain more than we imagine. But let's go smaller still. Stars are one thing, planets another. But what about individual atoms? What about the basic building blocks of matter, drifting through intergalactic space? We've already discussed the intergalactic medium, the diffuse gas that fills the cosmic web. But I want to spend more time on this because it's one of the most overlooked and underappreciated components of the universe. Think about a single hydrogen atom floating in intergalactic space. This atom, just one proton and one electron, is ancient beyond imagining. It was created in the first few minutes after the Big Bang, during the period of primordial nucleosynthesis, when the universe was still hot enough to forge atomic nuclei. That was 13.8 billion years ago. For most of the time since then, this atom has been drifting through space. It's been part of gas clouds. It's been ionized by ultraviolet radiation, losing its electron, only to recapture another 1 millions of years later. It's been heated by distant quasars and cooled by the expansion of the universe. Perhaps for a brief period, it was part of a star. Perhaps it fused with other hydrogen atoms to form helium, deep in a stellar core. Or perhaps it was always on the outskirts, never quite falling into a galaxy, always hovering in the cosmic web. Now it drifts through a void. The nearest galaxy is 5 million light-years away. The nearest other atom is a meter distant an eternity at the atomic scale. And yet, even in this isolation, the atom is not alone. It's bathed in light. Not much. The intergalactic radiation field is incredibly faint, but it exists. Photons from distant quasars, from ancient galaxies, from the cosmic microwave background itself, all pass through the void. Some interact with our lone atom, exciting its electron to higher energy levels, ionizing it entirely, keeping it connected to the distant universe. It's also affected by gravity. Dark matter halos, invisible but massive, shape the fabric of space around it. The expansion of the universe, driven by dark energy, carries it along. Even across the unimaginable distances of intergalactic space, nothing is truly isolated. But what about the most extreme wanderers of all? I'm talking about black holes. We know that galaxies contain supermassive black holes at their centers. We know that smaller black holes form when massive stars collapse. And we've recently learned that black holes can be ejected from galaxies. When two galaxies merge, their central black holes eventually find each other and spiral together. In the final moments before they merge, they emit enormous amounts of energy as gravitational waves. If this emission is asymmetric, if more gravitational waves go in one direction than another, the merged black hole can receive a powerful kick. This kick can be strong enough to eject the black hole from its galaxy entirely. Simulations suggest that this happens frequently. Over the history of the universe, many supermassive black holes may have been kicked into intergalactic space. They're out there now, wandering the void. A wandering supermassive black hole would be invisible in ordinary light. It emits nothing detectable unless it's actively consuming matter. But it would still distort the light of background objects through gravitational lensing. It would still shape the motion of anything that wandered near. It would be a phantom of the deep, an invisible monster cruising through the emptiness. We haven't detected any intergalactic supermassive black holes directly. The challenge is immense. How do you find something that's invisible, silent, and millions of light years away? But scientists are developing new techniques, including gravitational wave detectors that might eventually sense the ripples from these cosmic wanderers. Coming up, we dive deeper into the cosmic web's structure. We explore what scientists have learned about the filaments, walls, and voids that define the universe's architecture. And we confront a question that has puzzled researchers for decades. Why is the universe structured this way? What is the significance of the cosmic web? But first, let's pause and reflect on what we've discovered. Intergalactic space, which once seemed like the ultimate emptiness, turns out to be populated with objects of all sizes. Stars that will never call any galaxy home. Planets drifting in eternal darkness. Atoms and particles scattered across unimaginable distances. Black holes prowling like silent sharks in the deep. The void is not empty. It's a wilderness, strange, sparse, and cold, but not lifeless. And understanding this wilderness helps us understand the universe itself. Let's zoom out even further. We've explored individual wanderers, stars, planets, atoms, black holes. We've examined the cosmic web, the filaments and voids that structure the universe on the largest scales. Now I want to ask a more fundamental question. Why does the universe look this way? Why are galaxies arranged in a web-like pattern? Why are there vast empty voids? Why do structures exist at certain scales and not others? Is there something special about the architecture of the cosmos? These are deep questions, and they lead us to the very edge of what science can tell us about intergalactic space. Let's start with something called the cosmological principle. This is one of the foundational assumptions of modern cosmology. It states that, on the largest scales, the universe is homogeneous and isotropic. Homogeneous means it has the same properties everywhere. Isotropic means it looks the same in all directions. This might seem to contradict what we've been discussing. After all, the cosmic web clearly has structure. Galaxies cluster in some places and are absent in others. How can the universe be homogeneous if it has filaments and voids? The key is the phrase, on the largest scales. Look at a patch of sky a few degrees across, and you'll see clumpiness galaxy clusters here, voids there. Look at a patch a few 100 million light years across, and you'll still see structure superclusters and great walls and cosmic features. But average over truly large scales billions of light years, and the clumpiness smooths out. The density of galaxies becomes uniform. The cosmic web, viewed from far enough away, becomes indistinguishable from a uniform distribution. This scale, where the universe starts to look the same everywhere, is called the homogeneity scale. Current observations suggest it's somewhere around 300 to 400 megaparsecs, roughly a billion light years. Beyond that distance, the universe is essentially the same everywhere. But within that scale, the structure is fascinating. The cosmic web has distinct components. Let's examine each one. First, clusters and superclusters. Galaxy clusters are the densest regions of the cosmic web. They contain hundreds to thousands of galaxies, all bound together by gravity. The Virgo cluster, the nearest large cluster to us, contains over 1,000 galaxies in a region about 15 million light-years across. The Coma cluster, which Fritz Zwicky studied to discover dark matter, is even richer. Superclusters are collections of clusters. The Laniakea supercluster, which contains our own Milky Way, includes about 100,000 galaxies spread across 520 million light-years. Despite being enormous, superclusters aren't gravitationally bound. They're too big, and the universe is expanding too fast. Over billions of years, the expansion will tear superclusters apart. Second, filaments. Filaments are the strands of the cosmic web-long, relatively narrow structures connecting clusters. They contain galaxies, but the galaxies are spread out along the length of the filament rather than concentrated in a single region. The Pisces-Cetus supercluster complex is one of the largest known filaments. It stretches about 1 billion light-years and contains multiple superclusters along its length. When we observe distant parts of the universe, we see filaments crossing the sky like cosmic rivers. Third, walls and sheets. Walls are two-dimensional structures, thin sheets of galaxies separating large voids. The Great Wall discovered by Geller and Hoekra was one of the first identified. The Sloan Great Wall, discovered in 2003, is even larger, about 1.4 billion light-years across. These walls aren't solid, of course. They're defined by the galaxies and gas that trace them, but they represent real structures, boundaries in the cosmic architecture. Fourth, voids. Voids are the emptiest regions of the universe. They're not completely empty. They contain galaxies, just far fewer than average, but they can be enormous. The Boat's void, one of the most famous, is roughly 330 million light-years in diameter and contains only about 60 galaxies, where you'd expect thousands. Recent research has found even larger voids. The Eridanus supervoid, possibly connected to a mysterious cold spot in the cosmic microwave background, might be 500 million light-years or more across. Together, these components, clusters, filaments, walls, and voids form the cosmic web. They create a universe that's structured like a sponge or a foam, with galaxies tracing the surfaces of vast, empty bubbles. But here's what's remarkable. This structure was inevitable. Starting from the initial conditions of the Big Bang, tiny quantum fluctuations stretched to cosmic scales during inflation, and adding gravity and the expansion of space, you get the cosmic web. It's not an accident or a coincidence. It's a direct consequence of physics. Computer simulations have confirmed this. Starting with the known properties of the early universe, the density fluctuations, the amounts of dark matter and baryonic matter, the rate of expansion, scientists can simulate billions of years of cosmic evolution. And the simulations produce cosmic webs that look remarkably like the real thing. This is one of the great triumphs of modern cosmology. We understand, at least in broad terms, why the universe looks the way it does. The cosmic web isn't mysterious, it's predictable. But there are still mysteries. One involves the missing baryon problem I mentioned earlier. For decades, astronomers couldn't find about half of the ordinary matter that should exist. We knew how much baryonic matter the Big Bang produced. But when we added up all the matter in stars, galaxies, and gas clouds, we came up short. The solution, as we discussed, was the warm, hot intergalactic medium gas heated to millions of degrees, floating in the filaments of the cosmic web. This gas is so hot and so diffuse that it barely emits detectable radiation. It hides in plain sight. In the late 2010s, astronomers finally began detecting this missing matter directly. Using X-ray telescopes and sophisticated analysis techniques, they found the warm, hot gas exactly where simulations predicted it should be. The missing baryons weren't missing, they were just hiding. Another mystery involves the nature of voids. For a long time, scientists assumed voids were simply regions where galaxy formation was suppressed. The density was too low. There wasn't enough matter to form many galaxies. Simple. But recent research suggests voids might be more interesting than we thought. Voids aren't completely empty of dark matter. They contain dark matter halos, just as clusters. The halos are simply smaller and less massive. These mini halos might host dwarf galaxies too faint to detect with current telescopes. Or they might be dark halos, structures containing dark matter, but no stars at all. The existence of dark halos in voids would have profound implications. It would mean the voids are populated with invisible structures, a hidden universe within the empty spaces. We don't know how many such halos exist or what their properties are. The mystery remains. There's also the question of void evolution. As the universe expands, voids grow larger. The matter at their edges, influenced by dark energy, is pushed outward. Over billions of years, voids merge and expand until they dominate the cosmic landscape. In the far future, tens or hundreds of billions of years from now, the voids will be the universe. The filaments will thin and break. Galaxy clusters will become isolated islands in a sea of expanding emptiness. And eventually, even those islands will fade as the last stars die and the universe slides toward its cold, dark conclusion. But that's a story for later. Right now, let's focus on a more immediate question. What can intergalactic space tell us about the nature of the universe itself? The answer is quite a lot. The cosmic microwave background, the radiation left over from the Big Bang, gives us a snapshot of the universe when it was about 380,000 years old. The distribution of galaxies gives us a snapshot of the universe today, 13.8 billion years later. But intergalactic space, with its gas and its structures, gives us a record of everything in between. When we observe distant quasars, their light passes through intergalactic space on its way to our telescopes. That light is absorbed by hydrogen clouds in the intergalactic medium clouds that existed billions of years ago, when the universe was young. By analyzing the absorption patterns, we can study the properties of intergalactic space at different cosmic epochs. This technique, called the Lyman alpha forest, has revolutionized our understanding of the early universe. It's shown us how the intergalactic medium evolved, how galaxies grew and merged, how the cosmic web formed and changed over billions of years. And it's revealed surprises. One surprise involves the reionization of the universe. For the first few 100 million years after the Big Bang, the universe was dark. The gas was neutral, meaning hydrogen atoms had captured electrons. Neutral hydrogen absorbs the ultraviolet light that would have come from the first stars and galaxies. Then something happened. The first stars and quasars began to form, and their intense radiation began ionizing the surrounding gas-knocking electrons free from hydrogen atoms. This process, called reionization, transformed the universe from opaque to transparent. We can see evidence of reionization in the Lyman alpha forest. Before reionization, the forest is dense lots of absorption from neutral hydrogen. After reionization, it thins out, as ionized hydrogen absorbs much less light. But the timing and nature of reionization remain uncertain. Did it happen smoothly, spreading out from the first galaxies like ripples in a pond? Or did it happen in patches, with ionized bubbles growing and merging until they filled the universe? Different models make different predictions, and the evidence is still being gathered. Another surprise involves the temperature of the intergalactic medium. For years, scientists assumed the IGM was relatively cold, perhaps a few thousand degrees. Hot enough to be ionized, but not dramatically hot. But observations revealed that the IGM is actually much hotter than expected, often millions of degrees. This heating comes from shocks, as gas flows into filaments and clusters, and from the radiation of quasars and other energetic sources. The hot IGM has implications for galaxy formation. Hot gas is harder to compress, so it's harder to form new stars. The IGM might be suppressing galaxy formation throughout the universe, keeping countless potential galaxies from ever coming into existence. But perhaps the most profound thing intergalactic space tells us about is the geometry of the universe itself. By measuring the cosmic microwave background, the distribution of galaxies, both shaped by the cosmic web, astronomers can determine the overall shape of space. Is the universe curved, like the surface of a sphere? Is it saddle-shaped, with negative curvature? Or is it flat, with no overall curvature at all? The answer, remarkably, is flat. Space, on the largest scales, appears to have exactly zero curvature. This is surprising, because there's no obvious reason why it should be flat. A curved universe is just as mathematically consistent as a flat one. Yet somehow, the universe chose flatness. This observation is one of the strongest pieces of evidence for cosmic inflation, the rapid expansion in the first fraction of a second after the Big Bang. Inflation naturally produces a flat universe, stretching any initial curvature until it becomes unmeasurable. The flatness we observe is a relic of that ancient, violent expansion. But I'm getting ahead of myself. We're discussing the present-day universe and its structures. Let's return to intergalactic space and ask another question. What can we learn from the void? Coming up, we explore the great cosmic voids in more detail. We examine what they contain, how they've changed over time, and what they tell us about the fate of the universe. And we confront a disturbing possibility, that the voids might contain something no one expected. Imagine falling into emptiness, not falling towards something, falling into nothing. No stars above you, no planets below. Just an endless expanse of blackness, broken only by the faint smudges of galaxies millions of light years away. This is what it would be like to drift into a cosmic void. Voids are the largest structures in the universe in terms of volume. While filaments and clusters get more attention, they're where the galaxies are. After all, voids make up most of the space in the cosmos. Current estimates suggest that voids account for perhaps 80% of the universe's volume. That's an astonishing number. If you were teleported to a random point in the universe, odds are you'd end up in a void. The cosmic web, for all its grandeur, is the exception rather than the rule. But voids aren't simple. They have structure, history, and mysteries that scientists are still working to understand. Let's start with the basics. A cosmic void is defined as a region with significantly fewer galaxies than average. The threshold varies depending on who you ask, but typically a void has less than 1/10 the average galaxy density. Some voids are even emptier. The Boat's void, for example, has only about 1/60th the average density. Voids are also spherical, roughly speaking. They're not perfect spheres gravity, and the expansion of the universe distort them into complex shapes, but they're more spherical than filaments are cylindrical. This is because voids expand outward in all directions, pushing matter away from their centers. The expansion of voids is driven by the difference in density between the void and its surroundings. Matter in a void feels less gravitational pull than matter in a filament or cluster, so it's easier for expansion to carry it outward. Over billions of years, voids have grown, emptying out their interiors and adding matter to their edges. This process is called void evolution, and it's been happening since shortly after the Big Bang. The initial density fluctuations, those tiny variations in the early universe included regions slightly less dense than average. These became the seeds of voids. As the universe expanded, these seeds grew into the vast empty spaces we observe today. But here's the interesting part. Voids aren't static. They're still evolving. Computer simulations show that voids merge over time. When two adjacent voids grow large enough, they eventually touch. The wall of galaxies between them thins and breaks. The voids merge into a single, larger void. This process has been happening throughout cosmic history, and it will continue into the far future. Eventually, most of the small and medium-sized voids will have merged into a few enormous supervoids. The cosmic web will simplify, its intricate structure smoothing out as expansion continues. But for now, the voids are diverse. They range in size from about 30 million light-years across to hundreds of millions of light-years. The Boat's void, mentioned earlier, is roughly 330 million light-years in diameter. The Eridanus supervoid might be even larger. What's inside these voids? Less than you might think, but more than nothing. Voids contain galaxies, just not many of them. These void galaxies are typically smaller and fainter than galaxies in denser environments. They're often blue, indicating ongoing star formation, while cluster galaxies tend to be red and dead, with little new star formation. This makes sense when you think about it. In dense environments, galaxies interact frequently. They merge, stripping each other of gas and shutting down star formation. In voids, interactions are rare. Galaxies can evolve in isolation, continuing to form stars for billions of years. Void galaxies are interesting laboratories for studying galaxy evolution. They let us see what happens when galaxies are left alone, when the environment doesn't interfere with their development. But void galaxies are just the tip of the iceberg. There's much more matter in voids than the galaxies represent. Dark matter, for instance. Voids contain less dark matter than dense regions, but they're not empty of it. Simulations show that voids are threaded with thin filaments of dark matter, connecting the rare galaxies. These dark matter filaments are far more tenuous than the grand structures of the cosmic web proper. They're like spider silk compared to steel cables, delicate, almost invisible, but present nonetheless. And scattered along these gossamer threads are dark matter halos, some large enough to host the faint void galaxies we can detect, others too small to have ever accumulated enough gas to form stars. These dark halos represent one of the great unsolved puzzles of cosmology. We know they should exist. Simulations predict millions of them in every void, but we've never directly observed one. They're too small to lens background light in detectable ways. They contain no stars to shine. They're pure dark matter, invisible against the invisible background of intergalactic space. If we could somehow detect these dark halos, it would tell us enormous amounts about the nature of dark matter itself. The number of small halos, their distribution, their density profiles, all of these depend on the specific properties of dark matter particles. Different theories make different predictions. Finding the halos would let us distinguish between theories. But for now, they remain theoretical constructs, ghosts haunting the emptiest regions of the universe. Beyond dark matter, voids contain ordinary matter too. The intergalactic medium extends into voids, though at even lower densities than in filaments. A cubic meter of void might contain only 1/10 of an atom, or even less. But across the vast volumes of the voids, this adds up. And there's something else in voids, something strange. In 2004, astronomers announced the discovery of a peculiar feature in the cosmic microwave background. In the direction of the constellation Eridanus, there was a region significantly colder than its surroundings. Not by much, only about 70 microkelvin colder, but the discrepancy was statistically significant and didn't match predictions. What could cause such a cold spot? One possibility was a supervoid. If a massive void lay between us and the cosmic microwave background, it could imprint a cold signature on the radiation passing through it. This is called the integrated Sachs-Wolf effect, and it's a real phenomenon. When light passes through a region where the gravitational potential is changing, as it would be in a void accelerated by dark energy, the light loses energy. It becomes slightly redshifted, slightly cooler. Astronomers went looking for the supervoid, and they found one. The Eridanus supervoid, confirmed in 2015, is one of the largest structures ever identified. It's roughly 1.8 billion light-years across a vast bubble of emptiness, containing perhaps 10,000 fewer galaxies than expected. It lies about 3 billion light-years away, in exactly the direction of the cold spot. Case closed? Not quite. When scientists did the calculations, they found that the Eridanus supervoid wasn't quite big enough or empty enough to explain the full magnitude of the cold spot. The integrated Sachs-Wolf effect it produced was real, but it accounted for only a fraction of the observed temperature deficit. Something else must be contributing. What that something might be remains one of the great mysteries of cosmology. Some scientists have proposed that the cold spot is simply a statistical fluke, an unlikely but not impossible random variation. Others have suggested more exotic explanations. A cosmic texture left over from a phase transition in the early universe, or even evidence of a collision with another universe. Yes, you read that correctly. Some physicists have proposed that the cold spot might be a bruise left by our universe bumping into a neighboring universe in the multiverse. The collision would have affected the cosmic microwave background in that region, leaving a lasting scar. This is highly speculative, and most scientists don't take it seriously yet. But the mere fact that such ideas are being discussed shows how mysterious voids can be. The emptiest regions of the universe might contain evidence for the most profound truths about reality. But let's step back from speculation and focus on what we know for certain. Voids are expanding. They're growing larger as the universe ages, their boundaries pushing outward, their interiors becoming ever emptier. This expansion is driven by dark energy, the mysterious force that's accelerating the universe's growth. In the future, the far, far future voids will dominate the universe entirely. The filaments connecting galaxy clusters will thin and break. The clusters themselves will become isolated islands, surrounded by ever-expanding seas of emptiness. And eventually, even those islands will fade as the last stars burn out and the universe slides toward its final state. But that's a story for later in our journey. For now, let's turn to another question about intergalactic space. What happens when things collide? Because despite the emptiness of the cosmic voids, collisions happen all the time in intergalactic space. Galaxies merge, clusters combine, gas streams crash together at millions of miles per hour. And when these collisions occur, they reveal secrets about the nature of intergalactic space that we could learn no other way. Coming up, we explore the violent side of intergalactic space. We witness galaxy collisions that take billions of years to unfold. We examine the shockwaves that heat gas to hundreds of millions of degrees. And we discover what happens when dark matter meets dark matter in the ultimate cosmic crash test. The universe appears serene from a distance. Look at a photograph of a galaxy, the graceful spiral arms, the peaceful glow of 100 billion stars, and you might think the cosmos is a place of tranquility, a celestial garden, slowly evolving over billions of years, untouched by violence or chaos. This impression is an illusion created by timescales we cannot comprehend. The truth is that intergalactic space is a battlefield. Galaxies are constantly crashing into each other. Galaxy clusters are merging in cataclysms that release more energy than any other event in the universe. And the intergalactic medium itself is churned and heated by shockwaves that span millions of light years. These collisions are slow by human standards. A galaxy merger might take 1 billion years from first approach to final coalescence. But on cosmic timescales, they're common, almost routine. Most large galaxies have experienced at least one major merger in their history. Many have experienced several. And these mergers don't just affect the galaxies involved. They reshape intergalactic space itself. Let's start with what happens when two galaxies collide. When galaxies approach each other, gravity does strange things. Tidal forces, differences in gravitational pull across the width of a galaxy, distort the galaxies into bizarre shapes. Spiral arms get stretched into long streamers. Stars are flung out of their orbits. Gas clouds are compressed and ignited into bursts of star formation. The famous antennae galaxies show this process in action. Two spiral galaxies are in the process of merging, about 45 million light-years from Earth. Long tails of stars and gas stretch away from the main bodies, giving the system its insect-like appearance. In the regions where the galaxies overlap, new stars are being born at a furious rate, hundreds of times faster than in the Milky Way. But here's what's remarkable about galaxy collisions. The stars almost never actually hit each other. Stars are tiny compared to the distances between them. Even in the densest regions of a galaxy, stars are separated by light years of empty space. When two galaxies merge, their stars pass by each other like two swarms of bees occupying the same space. Individual collisions are incredibly rare. Gas, however, is a different story. Gas clouds can and do collide. When they do, they compress and heat up. The compression triggers star formation. The heating sends shockwaves through intergalactic space, and matter is expelled. During a galaxy merger, enormous amounts of gas are thrown out of the interacting galaxies. This gas doesn't disappear. It becomes part of the intergalactic medium. It joins the cosmic web, adding to the diffuse material that fills the space between galaxies. In some cases, the expelled material forms visible structures. Tidal tails, long streamers of stars and gas, can extend for hundreds of thousands of light years. Some of this material eventually falls back into the merged galaxy. Some escapes into intergalactic space forever. Stars are expelled too. Remember the intergalactic stars we discussed earlier? Many of them were born in galaxies, but ejected during mergers. They now wander the void, forever separated from any galactic home. But galaxy-galaxy collisions are small potatoes compared to what happens when galaxy clusters collide. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds to thousands of galaxies, enormous halos of dark matter, and vast quantities of hot gas. When two clusters collide, the result is the most energetic event in the universe since the Big Bang. The most famous example is the Bullet Cluster, about 3.8 billion light-years from Earth. The Bullet Cluster is actually two clusters in the process of colliding. About 150 million years ago, one cluster passed through the other at a speed of about 10 million miles per hour. The collision produced effects that revolutionized our understanding of dark matter. Here's what happened. The galaxies in each cluster passed through each other without slowing down much. Galaxies, like stars, are mostly empty space. They interacted gravitationally, but didn't physically collide. The hot gas in each cluster, however, was a different story. Gas interacts with itself through electromagnetic forces. When the gas clouds collided, they slammed into each other like two fast-moving clouds of smoke. They compressed, heated up, and slowed down dramatically. The gas from both clusters is now concentrated in the middle of the collision, trailing behind the galaxies. And the dark matter? Dark matter doesn't interact with itself through electromagnetic forces. It only interacts through gravity. So the dark matter halos of the two clusters passed right through each other, barely affected by the collision. The dark matter is now concentrated around the galaxies, ahead of the gas. We can see this separation clearly. X-ray telescopes reveal the hot gas concentrated in the center. Gravitational lensing reveals the dark matter concentrated on either side around the galaxies. The bullet cluster is a cosmic separation experiment, pulling apart the components of galaxy clusters and showing us what they're made of. And this separation provides some of the strongest evidence that dark matter exists. Before the bullet cluster, some scientists proposed that dark matter wasn't real, that instead, our understanding of gravity was wrong. Perhaps gravity worked differently on galactic scales than on the scales of laboratory experiments. Perhaps what we attributed to dark matter was really a modification of Newtonian mechanics. The bullet cluster put this theory to the test. If modified gravity were the explanation, the gravitational lensing should be centered on the gas. That's where most of the ordinary matter is. But the lensing is centered on the galaxies, where the dark matter would be if dark matter exists. The result was clear. Dark matter is real. It's not a modification of gravity. It's actual stuff, separate from ordinary matter, that passed through the collision while ordinary matter got stuck in the middle. The bullet cluster collision also produced enormous shock waves. When gas clouds collide at millions of miles per hour, they create shocks that heat the gas to hundreds of millions of degrees, far hotter than the core of the sun. These shocks propagate through intergalactic space, carrying energy and momentum far from the collision site. We can observe these shocks with X-ray telescopes. They appear as sharp edges in the temperature and density of the intergalactic gas. The shocks in the bullet cluster extend for millions of light years, far beyond the galaxies themselves. And here's something remarkable. These shocks might be factories for cosmic rays. Cosmic rays are high-energy particles, protons, electrons, and atomic nuclei that travel through space at nearly the speed of light. When they hit Earth's atmosphere, they create showers of secondary particles that we can detect at ground level. The most energetic cosmic rays have energies far beyond anything we can achieve in particle accelerators on Earth. Where do cosmic rays come from? Some come from the sun. Some come from supernova remnants in our galaxy. But the most energetic cosmic rays, the ultra-high energy cosmic rays, seem to come from outside the Milky Way. And cluster collision shocks are one of the leading candidates for their origin. Here's how it might work. When gas clouds collide, particles can get trapped in the shock region. They bounce back and forth across the shock front, gaining energy with each crossing. Over millions of years, some particles reach extraordinary energies, tens of millions of times higher than anything at the Large Hadron Collider. These particles then escape into intergalactic space, becoming the cosmic rays that occasionally strike Earth's atmosphere. If this theory is correct, then cluster collisions are not just spectacular events. They're cosmic particle accelerators, filling intergalactic space with the most energetic particles in the universe. But collisions do more than create shockwaves and cosmic rays. They also reveal the structure of intergalactic space in ways that nothing else can. When clusters collide, their gas is compressed and heated. This hot gas glows in X-rays, revealing details of the intergalactic medium that we couldn't see otherwise. The shapes of the shocks tell us about the properties of the gas, its temperature, density, and motion. The distribution of dark matter tells us about the behavior of this mysterious substance. In recent years, astronomers have found many more colliding clusters. Each one is a natural laboratory, revealing different aspects of intergalactic physics. The Abel 520 cluster, for instance, shows a dark matter core that seems to have separated from the galaxies, the opposite of what we'd expect from simple dark matter theories. The El Gordo cluster is one of the most massive colliding systems ever found, challenging our models of structure formation. And the collisions continue. Right now, countless clusters across the universe are in the process of merging. Galaxy groups are falling into larger clusters. Filaments are funneling matter toward dense nodes of the cosmic web. The universe is not static. It's a dynamic, evolving system where structures grow through collision and merger. Even our own local group is not immune. In about 4 to 5 billion years, the Andromeda Galaxy will collide with the Milky Way. The two galaxies will merge over the following billion years, their stars passing through each other, their gas clouds colliding and compressing, their supermassive black holes eventually merging in a burst of gravitational waves. When this happens, countless stars will be expelled into intergalactic space. The gas between the galaxies will be heated and ionized. New stars will form in the compressed regions. And eventually, a single, larger galaxy will emerge, sometimes called Milkomeda or Milkdromeda by astronomers, with a flair for the dramatic. But this future collision raises an interesting question. What happens to life during a galaxy merger? The answer, surprisingly, is probably not much. Remember, stars almost never collide during mergers. The sun might change its position within the merged galaxy. It might end up in the outer regions, or even be expelled into intergalactic space. But the odds of a direct collision with another star are negligible. Earth would continue orbiting the sun, largely unaffected by events happening light years away. The real changes would be visible in the night sky. As Andromeda approached, it would grow larger and brighter, eventually dominating the heavens. The orderly spiral structure of both galaxies would dissolve into chaos during the merger. But from the surface of Earth, this would be a spectacular show. Not an existential threat? Of course, by the time the merger happens, the sun will be in the later stages of its life. Earth might not be habitable anyway, but that's a different story. Coming up, we turn from collisions to something even more extreme. We explore the radiation that permeates intergalactic spacelight, cosmic rays, and other forms of energy that fill the void between galaxies. And we discover that even the emptiest regions of the universe are constantly bathed in a sea of invisible radiation. Close your eyes and imagine you're floating in the void between galaxies. What do you perceive? If you're imagining complete darkness, complete silence, complete emptiness, you're wrong. Intergalactic space is not empty of energy. It's filled with radiation photons of every wavelength, from radio waves to gamma rays, permeating the void in all directions. If you had instruments sensitive enough, you would detect a constant buzz of light and particles, even in the deepest void. This radiation comes from many sources. Some is ancient leftover from the Big Bang itself. Some is relatively recent, produced by stars and galaxies and quasars. Some is mysterious, its origins still unclear. Together, this radiation forms the extragalactic background light, the total amount of light in the universe beyond our own galaxy. And studying this background reveals secrets about intergalactic space that we could learn no other way. Let's start with the oldest light in the universe, the cosmic microwave background. We've mentioned the CMB several times already, but it deserves a deeper exploration. This radiation is the afterglow of the Big Bang light released about 380,000 years after the universe began, when it had cooled enough for atoms to form and photons to travel freely through space. When this light was released, it was incredibly hot, about 3,000 degrees Kelvin. But over the past 13.8 billion years, as the universe has expanded, this light has stretched and cooled. Today, it has a temperature of just 2.725 Kelvin, less than 3 degrees above absolute zero. This radiation is everywhere. No matter where you are in intergalactic space, the CMB surrounds you. It comes from all directions equally, filling the universe with a faint, uniform glow. The energy in the CMB is small, but not negligible. If you added up all the photons in the CMB, they would contribute about 400 photons per cubic centimeter of space, anywhere in the universe. These photons carry the memory of the early cosmos, a snapshot of conditions just a few 100,000 years after everything began. But the CMB isn't the only ancient radiation in intergalactic space. There's also the cosmic neutrino background, a sea of neutrinos released even earlier than the CMB, when the universe was about 1 second old. These neutrinos are even cooler than the CMB photons, with an effective temperature of about 1.95 Kelvin. They're also incredibly difficult to detect because neutrinos barely interact with ordinary matter. We haven't directly detected the cosmic neutrino background yet. The technology doesn't exist. But we know it's there. The physics demands it. About 330 neutrinos per cubic centimeter fill every corner of intergalactic space, invisible witnesses to the earliest moments of cosmic history. Beyond these ancient relics, intergalactic space is filled with light from more recent sources. The infrared background comes from dust and stars in distant galaxies. When stars emit light, some of it is absorbed by dust, which re-radiates the energy at infrared wavelengths. This infrared light accumulates over cosmic time, creating a diffuse glow that permeates intergalactic space. The optical and ultraviolet background comes from stars and quasars. Every star in every galaxy emits light, and some of that light escapes into intergalactic space. It joins the growing sea of photons adding to the extragalactic background. The X-ray background comes from hot gas in galaxy clusters and from active galactic nuclei, i.e. the brilliant cores of galaxies where supermassive black holes are devouring matter. These high-energy sources fill intergalactic space with a faint but detectable X-ray glow. And the gamma-ray background remains partially mysterious. Some of it comes from known sources, blazars, pulsars, supernova remnants. But some of it might come from exotic sources, dark matter annihilation, for instance, or processes we haven't yet identified. When you add up all these contributions, you get a remarkable picture. Intergalactic space is not dark. It's filled with light at every wavelength. We don't perceive this light because our eyes aren't sensitive enough, and the intensity is far below what we can detect. But it's there, a cosmic ocean of radiation in which everything in the universe swims. But photons aren't the only radiation in intergalactic space. There are also particles. We've already discussed cosmic rays, high-energy particles that streak through the universe at nearly the speed of light. These particles come from violent events, supernova explosions, neutron star collisions, the shocks of colliding galaxy clusters. They fill intergalactic space with a constant rain of protons, electrons, and heavier nuclei. The density of cosmic rays in intergalactic space is very low. In the emptiest voids, you might wait years for a single cosmic ray to pass through a given cubic meter. But they're there, carrying energy across billions of light years, occasionally striking planets and moons, and even spacecraft. Cosmic rays are important for several reasons. First, they're a window into extreme physics. The most energetic cosmic rays have energies beyond anything we can create on Earth. Studying them tells us about the most violent events in the universe. Second, they affect the chemistry of intergalactic space. When cosmic rays pass through gas clouds, they ionize atoms and molecules. This ionization triggers chemical reactions that wouldn't happen otherwise. Even in the sparse intergalactic medium, cosmic rays are catalysts for chemistry. Third, cosmic rays might affect life. On Earth, our atmosphere and magnetic field protect us from most cosmic rays. But on worlds without such protection, cosmic rays could pose a significant radiation hazard. For any life in intergalactic space orbiting an intergalactic star, for instance, cosmic rays would be a constant threat. There's another form of radiation in intergalactic space that we haven't yet discussed: gravitational waves. Gravitational waves are ripples in space-time itself, produced when massive objects accelerate. They were predicted by Einstein in 1916 and finally detected in 2015 when the LIGO observatories sensed the merger of two black holes over 1 billion light-years away. Since then, we've detected many more gravitational wave events: merging black holes, merging neutron stars, perhaps merging objects of kinds we haven't identified. And these waves don't just pass through intergalactic space, they fill it. Every gravitational wave event sends ripples propagating outward at the speed of light. These ripples never stop. They stretch and fade as the universe expands, but they persist forever. Over the history of the universe, countless events have produced gravitational waves, black hole mergers, neutron star collisions, the violent births and deaths of stars, perhaps exotic events in the early universe that we don't yet understand. All of these events have contributed to a stochastic gravitational wave background, a sea of overlapping ripples filling all of space. We haven't directly detected this background yet, though pulsar timing arrays are beginning to sense its effects. But we know it exists. It must, given the physics involved. Imagine floating in intergalactic space with a gravitational wave detector. You wouldn't sense a single clear signal. You'd sense a constant, chaotic chorus of ripples from countless sources. The universe vibrating, humming with the accumulated energy of billions of years of cosmic violence. This is what intergalactic space is really like. Not silent, not still, but filled with radiation of every kind: electromagnetic, particulate, gravitational. A sea of energy in which matter floats like islands in an ocean. But there's one more form of radiation we should discuss, and it's perhaps the strangest of all. Dark energy. We've talked about dark energy as the force driving the acceleration of cosmic expansion. But in some theories, dark energy isn't just a force. It's a form of energy that fills space. The cosmological constant, which is the simplest model of dark energy, describes a constant energy density throughout the universe. Every cubic meter of space, anywhere in the cosmos, contains the same amount of dark energy. This energy doesn't radiate in the conventional sense. It doesn't produce photons or particles. But it's there, contributing to the total energy content of the universe. In fact, it's the dominant form of energy, making up about 68% of everything. If dark energy is a property of space itself, then intergalactic space, where space is most abundant, is where dark energy is most prominent. The voids, which contain relatively little matter and radiation, are almost pure dark energy. They're the closest thing in the universe to empty space, and therefore the closest thing to pure dark energy. This is a strange thought. The emptiest regions of the cosmos are actually the fullest full of a mysterious energy we don't understand, driving the universe toward an uncertain future. Coming up, we explore that future. We ask what will happen to intergalactic space over billions and trillions of years. We trace the fate of the cosmic web, the death of the last stars, and the ultimate destiny of the universe. What we find will be both sobering and, in its own way, beautiful. Everything ends. This is a truth that humans have grappled with since we first became conscious of our own mortality. We see endings all around us: the setting of the sun, the falling of leaves, the death of loved ones. Endings are woven into the fabric of our experience. But what about the universe itself? Does it have an ending? And if so, what happens to intergalactic space, the vast emptiness between galaxies, as that ending approaches? The answer, as far as current physics can tell us, is both simple and profound. Yes, the universe will end. Not in a cosmic cataclysm, not in a dramatic collapse, but in a slow, inexorable fade. A heat death that will take trillions upon trillions of years to unfold. And intergalactic space will be where it happens. Let me explain. The universe is expanding. It has been expanding since the Big Bang, and thanks to dark energy, that expansion is accelerating. Every year, The space between distant galaxies grows larger. The voids grow emptier. The filaments of the cosmic web grow thinner. In the near future, the next few billion years, this expansion will have visible effects. Distant galaxies will recede beyond our cosmic horizon. The light from these galaxies will become stretched and redshifted, eventually becoming undetectable. One by one, the galaxies we can see today will fade from view. In about 150 billion years, almost all galaxies beyond our local group will have disappeared over the horizon. The night sky will grow darker. The universe, as seen from our corner of space, will appear to contain only a single large galaxy, the merged remnant of the Milky Way and Andromeda, along with whatever smaller galaxies have fallen into it by then. This isn't the end of those distant galaxies, of course. They still exist, but the expanding space between us will make them forever unreachable, forever unobservable. We will be isolated in an island of visibility, surrounded by an infinite dark sea. But even our local island has a finite lifespan. Stars burn out. The sun will exhaust its hydrogen fuel in about 5 billion years, swelling into a red giant before collapsing into a white dwarf. This fate awaits most stars in the universe. Over tens of billions of years, the bright stars will die one by one, leaving behind stellar corpses, white dwarfs, neutron stars, black holes. New stars can form, but only as long as there's gas to form them from. And galaxies are constantly losing gas to star formation, to galactic winds, to stripping by the intergalactic medium. Eventually, the supply runs out. The last stars flicker into existence and then burn out. The galaxies go dark. Current estimates suggest that the era of star formation will end in about 100 trillion years. That's 100 trillion years from now, a span of time so vast that our current 13.8 billion years of cosmic history is a mere eye blink in comparison. After that, the universe will be dark, no stars, no sunlight, just the fading glow of white dwarfs, cooling over trillions of years, and the invisible presence of black holes, neutron stars, and the diffuse gas of the intergalactic medium. But even this dark era won't last forever. White dwarfs cool. They radiate their remaining heat into the void, growing dimmer and dimmer. After about a quadrillion years, a million billion years, they will have faded to black dwarfs, objects with the mass of stars, but no light at all. Neutron stars cool too. They have less energy to radiate than white dwarfs, so they'll fade faster. But they'll still exist, dark and dense, spinning slowly down over the eons. And black holes? Black holes might seem eternal, but they're not. Stephen Hawking showed in the 1970s that black holes emit radiation, a quantum mechanical process called Hawking radiation. This radiation carries energy away from the black hole, causing it to slowly evaporate. For stellar mass black holes, this evaporation is extraordinarily slow. A black hole with the mass of our Sun would take about 1,067 years to evaporate, a 1 followed by 67 zeros. For supermassive black holes, the timescale is even longer, 10,100 years or more. But eventually, Even black holes will evaporate. The last black hole will emit its final burst of Hawking radiation and vanish. And then the universe will be truly empty. Not just intergalactic space, all of space. The cosmic web will have dissolved. The galaxies will have disintegrated. The stars will have burned out and faded. Even the black holes will have evaporated. What remains will be a thin, cold gas of elementary particles spread across an infinitely expanding space. Electrons and positrons, protons and neutrons, photons and neutrinos, all drifting apart as the universe expands forever, growing colder, becoming ever more diffuse. This is the heat death of the universe. It's not a dramatic ending, no big crunch, no final explosion. Just a slow fade into eternal darkness and cold. The temperature of this final universe will approach absolute zero, but never quite reach it. The cosmic microwave background will continue to cool as space expands. The energy of the particles will diminish. Time, in a sense, will cease to have meaning. Nothing will happen. Nothing will change. Nothing will differentiate one moment from the next. This is the fate of intergalactic space. It's also the fate of everything else. But I want to step back from this bleak picture and offer some perspective. First, we're talking about timescales that dwarf anything in human experience. 100 trillion years until the last star. 10 to the 100th power years until the last black hole. These numbers are so large that they're essentially meaningless. No one will experience this ending, not because intelligence won't survive, but because there's so much time before it happens that anything could occur. Second, our understanding of physics might be incomplete. The heat death scenario assumes that our current theories are correct, that the universe will keep expanding, that protons are stable, that dark energy behaves the way we think. But physics has surprised us before. There might be new phenomena that emerge on these vast timescales, processes we haven't yet discovered. Third, even in the face of cosmic doom, there's beauty. The universe has given rise to stars and galaxies, to planets and life, to consciousness and wonder. Whatever happens in the far future, what has already happened is remarkable. The fact that we're here, pondering the fate of the cosmos, is itself a kind of miracle. And finally, intergalactic space, the emptiness between galaxies, teaches us something profound about existence itself. Most of the universe is empty. Most of space contains nothing or almost nothing. The galaxies we see, the stars we admire, the planets we dream of visiting, all of this represents a tiny fraction of the cosmos. The vast majority is void. And yet, that void is not nothing. It contains gas and dark matter. It contains radiation and gravitational waves. It contains the scaffolding on which all structure is built. Without intergalactic space, galaxies couldn't exist. Without the cosmic web, stars couldn't form. The emptiness is essential. Perhaps there's a lesson here. Perhaps the emptiness between things is as important as the things themselves. Perhaps meaning arises not just from matter, but from the spaces between matter, from the relationships, the connections, the distances that define our existence. But I'm waxing philosophical. let me return to more concrete territory. Coming up, we explore one of the most profound questions we can ask about intergalactic space. Could anything live there? Is the void between galaxies truly hostile to life? Or might it harbor possibilities we haven't yet imagined? Here's a question that haunts every exploration of the cosmos. Are we alone? We've asked this question while studying Mars, searching for microbes in ancient riverbeds. We've asked it while examining the icy moons of Jupiter and Saturn, imagining life in their hidden oceans. We've asked it while listening for radio signals from distant stars, hoping for a message from an alien civilization. But rarely do we ask this question about intergalactic space. The void between galaxies seems too hostile, too empty, too extreme. Surely nothing could survive out there, let alone thrive. But let's examine this assumption. Let's ask seriously, could life exist in intergalactic space? To answer this, we need to understand what life requires. On Earth, life depends on three things: energy, chemistry, and time. Energy drives biological processes, whether from sunlight, chemical reactions, or geothermal heat. Chemistry provides the raw materials: carbon, hydrogen, oxygen, nitrogen, and dozens of other elements that combine to form the molecules of life. Time allows evolution to work its magic, building complexity, adapting to environments, creating diversity. Does intergalactic space have these ingredients? Let's start with chemistry. We've established that intergalactic space is not truly empty. The intergalactic medium contains hydrogen, helium, and trace amounts of heavier elements. These elements are sparse, perhaps 1 atom per cubic meter, but they exist. However, this is far too sparse for any chemistry resembling what we see on Earth. Chemistry requires atoms to meet and interact. In intergalactic space, atoms are so far apart that they rarely encounter each other. The timescales for chemical reactions would be astronomical, literally. So the diffuse intergalactic medium is probably not a good candidate for life. The raw materials are there, but they're too spread out to do anything useful. But what about denser environments? What about the intergalactic stars and planets we discussed earlier? Here, things get more interesting. An intergalactic star with planets could potentially support life just as well as a star within a galaxy. The star provides energy. The planets provide solid surfaces or liquid oceans. The chemistry can proceed just as it does in galactic systems. The challenge isn't the host star, it's everything else. Consider the origin of life. On Earth, life arose from the primordial soup of our young planet, powered by energy from the sun and perhaps from volcanic vents. The raw materials were abundant. The environment was dynamic. Over hundreds of millions of years, chemistry became biology. But where did those raw materials come from? The carbon, oxygen, nitrogen, and phosphorus that make up our bodies weren't present at Earth's formation. They were delivered later by asteroids and comets debris left over from the formation of the solar system. This debris came from the protoplanetary disk that surrounded our young sun, and that disk was enriched with heavy elements from generations of previous stars that exploded as supernova, spreading their nuclear ash across interstellar space. A planet orbiting an intergalactic star might have less access to this enrichment. If the star was ejected from its galaxy early in its life, its planets might lack the heavy elements needed for complex chemistry. Life might be harder or impossible to get started. But not all intergalactic stars are pristine. Some were ejected with their planets already formed. Some came from the cores of their parent galaxies, where heavy elements were abundant. These stars and planets might carry the ingredients for life with them into the void. So it's possible, not likely, but possible that life could exist on planets orbiting intergalactic stars. What would such life be like? It would be profoundly isolated. The nearest other star might be hundreds or thousands of light years away. If intelligent life evolved on such a world, it would look out at a sky almost devoid of stars, just its parent sun and the faint smudges of distant galaxies. Any civilization that developed on an intergalactic planet would face extraordinary challenges. Communication with other beings would be all but impossible. The distances are too vast, the travel times too long. They might never know if they were alone in the universe, or one of countless civilizations scattered across the cosmos. This isolation might shape their culture and psychology in ways we can barely imagine. Would they be more introspective, focused on inner worlds rather than outer exploration? Would they feel a profound loneliness, gazing at unreachable galaxies? Or would they find meaning in their solitude, developing philosophies that embrace their unique place in the universe? We can only speculate. But there's another possibility for life in intergalactic space one that doesn't require stars at all. Remember the rogue planets we discussed? Worlds ejected from their solar systems, drifting through the darkness without a sun? These planets are frozen on the surface, colder than any world we know. But some might have internal heat from radioactive decay or tidal forces that keep subsurface oceans liquid. Could life evolve in these hidden oceans? On Earth, we found life in the most extreme environments. Bacteria thrive in the boiling waters of hydrothermal vents. Microbes live in solid rock miles below the surface. Fish swim in the frozen waters beneath Antarctic ice. Life, it seems, is remarkably adaptable. A rogue planet with a subsurface ocean might be similar to Europa or Enceladus, except utterly alone, surrounded not by the ice of an outer solar system, but by the vacuum of intergalactic space. If life could evolve in such an ocean, it would never see the stars. It might never know that space existed. Its entire universe would be the dark waters of its hidden sea. This is a haunting thought. Trillions of rogue planets might drift through intergalactic space. Some fraction might have subsurface oceans. Some fraction of those might host life. There could be entire biospheres out there, alien ecosystems evolving in eternal darkness that we will never detect, never contact, never know about. The universe might be teeming with life that is forever hidden from us. But let's push further. What about life that doesn't require planets at all? This is where we enter the realm of pure speculation, but it's worth considering. Some scientists have proposed that life might take forms radically different from anything we know. Instead of biological life based on carbon chemistry, There might be life based on plasma interactions in the outer layers of stars. There might be life based on nuclear reactions in the cores of neutron stars. There might be life based on something we haven't thought of yet. Could intergalactic space support such exotic life? It's hard to say. We have no evidence that such life exists. We have no theoretical framework for how it would function. But intergalactic space is vast and strange, and we should be humble about what we claim to know. There's one more possibility I want to mention. Artificial life? If intelligent civilizations exist, they might eventually develop the ability to leave their home galaxies. They might construct ships or habitats capable of crossing the intergalactic void journeys that would take millions of years, even at significant fractions of the speed of light. Or they might send probes, robotic explorers designed to survive the long journey between galaxies. These probes might be sophisticated enough to count as artificial life, replicating and evolving as they traverse the cosmos. In this scenario, intergalactic space might be crossed by fleets of ancient probes, launched by civilizations that have long since died or evolved beyond recognition. These probes would carry the legacy of their creators across billions of light years, kind of interstellar seeding that transcends the limits of biological life. We have no evidence that this has happened. But the universe is old, and the distances involved ensure that even a single probe would take millions of years to reach us. They could be out there, drifting through the void, and we would have no way of knowing. Let me pause here and acknowledge the obvious. This is all speculation. We have no evidence that any form of life exists in intergalactic space. We have no evidence that life exists anywhere beyond Earth, for that matter. Everything I've discussed in this chapter is a possibility, not a probability. But that's part of what makes the question so fascinating. Intergalactic space is the largest environment in the universe. If life can exist anywhere in the cosmos, shouldn't we at least consider whether it could exist there? And even if intergalactic space is truly lifeless, even if we're the only life in our galaxy, and the voids are empty, understanding why teaches us something important. It teaches us about the conditions that life requires. It teaches us about the limits of biology. It teaches us about our own remarkable existence on this small, warm, richly endowed planet. Coming up, we explore the ultimate implications of intergalactic space. We ask what it means that most of the universe is empty. We grapple with questions of meaning, significance, and our place in the cosmic order. And we confront the deepest mystery of all. Why is there something rather than nothing? We've journeyed far together. We've traveled from the familiar shores of our home galaxy into the vast reaches of intergalactic space. We've explored the cosmic web, the dark matter halos, the wandering stars and planets. We've witnessed the violent collisions of galaxy clusters and peered into the far future when even black holes will have evaporated. Now, I want to step back and ask a different kind of question. Not a scientific question, but a philosophical one. What does it mean that most of the universe is empty? Consider the following. If you were randomly teleported to any point in the observable universe, the odds that you'd find yourself near a star, a planet, or any significant amount of matter are vanishingly small. you'd almost certainly appear in the deep void between galaxies, surrounded by almost nothing, millions of light years from the nearest substantial object. The universe, in other words, is almost entirely uninhabited, not just by life, but by anything. The galaxies we study, the stars we admire, the planets we dream of exploring, all of this represents a tiny fraction of the cosmos. A few specks of matter floating in an almost infinite ocean of emptiness. This fact has profound implications for how we understand our place in the universe. Throughout history, humans have tended to see ourselves as central to creation. The Earth was the center of the cosmos. The sun revolved around us. The stars were put in the sky for our benefit. This geocentric, anthropocentric view was shattered by the discoveries of Copernicus, Galileo, and their successors, but its echoes persist. Even today, when we look at the night sky, we tend to focus on the stars. We imagine other worlds, other civilizations, other forms of life. We dream of exploring the galaxy, making contact with alien beings, becoming a spacefaring species. But intergalactic space reminds us that the universe is not built for us. The vast majority of the cosmos is hostile to life as we know it. The temperatures are either too hot or too cold. The radiation is too intense or too sparse. The matter is too diffuse for chemistry to occur. The distances are too vast to ever be crossed. We exist in a tiny, privileged bubble planet orbiting a stable star in a galaxy rich with heavy elements in a relatively dense region of the cosmic web. If we were moved to almost any other location in the universe, we would die instantly. This is a humbling realization. It challenges our intuitive sense that the universe exists for a purpose, that we're meant to be here, that our existence is somehow central to the cosmic story. And yet, here we are, against all odds, in a universe that is almost entirely empty and hostile. Matter has organized itself into stars and planets and people. Chemistry has become biology. Biology has become consciousness. Consciousness has become curiosity. We exist. We're here, pondering these questions. Isn't that remarkable? There's a famous thought experiment called the anthropic principle. It observes that the universe must be compatible with the existence of observers, because if it weren't, we wouldn't be here to observe it. This sounds tautological, and in a sense it is, but it points to something important. The fact that the universe is mostly empty doesn't mean the empty parts are more important or more real than the parts with matter and life. We observe the universe from the inside, from a position of consciousness and existence. Our perspective is shaped by the fact that we're here. Some philosophers have argued that consciousness might be more fundamental than matter, that the universe is structured in such a way that consciousness inevitably arises. If this is true, then the vast empty spaces of intergalactic void might be less central to the cosmic story than they appear. The real story might be happening in the tiny pockets where matter has organized itself into aware, thinking beings. This is a controversial view, and I'm not advocating for it, but it's worth considering as we grapple with the meaning of intergalactic emptiness. There's another philosophical perspective worth mentioning: the absurd. The existentialist philosopher Albert Camus wrote about the absurd, the conflict between our desire for meaning and the apparent meaninglessness of the universe. Looking at intergalactic space, we might feel this absurdity acutely. Here is a cosmos almost entirely devoid of anything we would recognize as significant. Here is emptiness on a scale that defies comprehension. Why? Camus' answer was not despair but defiance. We can create our own meaning, he argued, even in the face of a meaningless universe. We can choose to live fully, to embrace our existence, to find joy in the limited time we have. Perhaps intergalactic space, in its vast emptiness, is a canvas on which we project our own meaning. It doesn't provide significance. We do. But there's another way to look at this. Intergalactic space is not meaningless. It's essential. Without the vast empty spaces, there would be no structure. The cosmic web requires voids as much as filaments. The galaxies that form at the nodes of the web are defined by the empty spaces between them. In a sense, the emptiness creates the fullness. The void gives form to matter. This principle appears throughout nature. Silence gives meaning to sound. Darkness gives meaning to light. Death gives meaning to life. Without contrast, without absence, the things that exist would have no definition. Perhaps intergalactic space is the cosmic equivalent of silence, the vast empty canvas that makes the galaxies stand out. That gives the universe its structure and beauty. There's also something profound about the sheer scale of intergalactic space. We are accustomed to thinking of large things as significant and small things as insignificant. A mountain is impressive. A pebble is not. A nation is important. An individual is less so. This scaling of significance shapes our intuitions about what matters. But intergalactic space challenges this intuition. Here are structures larger than anything we can comprehend, cosmic walls, billions of light years long, voids that could contain millions of galaxies. And yet, these structures are essentially empty. They contain almost nothing of interest. They're significant in size, but apparently insignificant in substance. Meanwhile, on tiny planets orbiting insignificant stars in unremarkable galaxies, life has arisen. Consciousness has evolved. Meaning has emerged. Perhaps size is not the measure of significance. Perhaps what matters is not how large something is, but what happens within it. A single thought in a human brain might be more significant in some cosmic sense than an entire supervoid spanning 500 million light years. This is a hopeful perspective. It suggests that we, small as we are, might matter more than the vast emptiness that surrounds us. It suggests that meaning is concentrated in the rare pockets of complexity, not spread thinly across the void. Of course, this might be wishful thinking. We want to believe we matter. We want to believe the universe has a purpose. Our desire for significance might be coloring our interpretation of the facts. But science cannot answer questions of meaning. It can tell us what exists and how it works. It cannot tell us why it exists or whether it matters. Those are questions for philosophy, for religion, for each of us to grapple with individually. What I can tell you is this: the universe is magnificent. Whether or not it has a purpose, whether or not we are significant, the cosmos is a wonder beyond description. The fact that emptiness and fullness coexist that order emerges from chaos. That matter organizes itself into galaxies and stars and planets and people. This is miraculous. Not miraculous in the supernatural sense, but miraculous in the sense of evoking awe and wonder. Intergalactic space, in its vastness and emptiness, is part of this wonder. It's the silent partner to the cosmic dance, the space between the notes, the pause between the heartbeats of the universe. And perhaps in the end, that's meaning enough. We've covered an enormous amount of ground in our journey tonight. We've explored the history of how humans discovered intergalactic space. We've examined the cosmic web and its components, filaments, walls, clusters, and voids. We've investigated dark matter and dark energy, the invisible forces that shape the cosmos. We've encountered wandering stars and rogue planets, cosmic rays and gravitational waves. We've pondered the far future of the universe and asked whether life might exist in the void. But as we approach the end of our exploration, I want to be honest with you about something. There is still so much we don't know. For all our scientific progress, for all the telescopes and satellites and computer simulations, intergalactic space remains deeply mysterious. We've made extraordinary advances in the past century, but we've also discovered that the universe is far stranger than we ever imagined. Let me highlight some of the biggest remaining mysteries. First, dark matter. We've talked extensively about dark matter. It makes up about 27% of the universe. It shapes the cosmic web. It holds galaxies together. And we have no idea what it is. Decades of experiments have failed to detect dark matter particles directly. The leading candidates, WIMPs, axions, sterile neutrinos, remain hypothetical. Every year, the constraints tighten, the parameter space shrinks, and we still haven't found it. Some scientists are beginning to wonder if we're on the wrong track entirely. Maybe dark matter isn't a particle. Maybe it's something else, a modification of gravity, a property of space-time, something we haven't thought of yet. Whatever the answer, it will profoundly change our understanding of intergalactic space. The scaffolding of the cosmic web is made of dark matter. If we don't know what dark matter is, we don't really know what the universe is made of. Second, dark energy. Dark energy is even more mysterious than dark matter. It makes up about 68% of the universe. It's causing the expansion of space to accelerate, and we have almost no idea what it is. The simplest explanation is the cosmological constant, a fixed energy density intrinsic to space itself. But this explanation raises its own problems. Why does the cosmological constant have the value it does? According to quantum field theory, the vacuum energy of space should be vastly larger than what we observe. This discrepancy by a factor of roughly 10,120 is sometimes called the worst prediction in the history of physics. Other theories propose that dark energy is dynamic, that it changes over time, perhaps varying in different parts of the universe. These theories are hard to test, but future observations might provide clues. Whatever dark energy turns out to be, it controls the fate of the universe. It determines whether the expansion will continue forever, whether it might eventually reverse, whether new physics might emerge on cosmological timescales. Understanding dark energy is one of the greatest challenges facing physics today. Third, the nature of space itself. We've talked about space as if it were a well-understood backdrop and empty stage on which the cosmic drama plays out. But the nature of space is itself mysterious. General relativity describes space as a dynamic entity curved by mass and energy. Quantum mechanics suggests that space might have a granular structure at the smallest scales, a quantum foam of fluctuating geometry. Some theories propose that space has additional dimensions beyond the three we perceive, dimensions that might be curled up too small to detect, or that might extend into realms we can't access. Intergalactic space, in its vastness and emptiness, might be the best laboratory for studying the nature of space itself. If space has subtle properties we haven't detected, quantum gravity effects, extra dimensions, vacuum fluctuations, they might be most apparent in the void. Fourth, the origin of everything. We've traced the cosmic web back to the Big Bang, explaining its structure as a consequence of inflation and gravity. But this raises deeper questions. What happened before the Big Bang? What caused the universe to come into existence? Why is there something rather than nothing? These questions might seem metaphysical, beyond the reach of science, but some physicists are trying to answer them. Theories of quantum cosmology propose that the universe might have emerged from a quantum fluctuation in a pre-existing vacuum. Theories of the multiverse suggest our universe might be one of countless universes, each with different properties. If the multiverse is real, intergalactic space might be just the beginning. The true void might be the space between universes, a metacosmic emptiness that makes intergalactic space look crowded by comparison. Fifth, our own ignorance. Perhaps the deepest mystery is how much we don't know that we don't know. Throughout history, scientific revolutions have revealed that our understanding was fundamentally incomplete. Before Einstein, we didn't know that space and time were aspects of a single entity. Before quantum mechanics, we didn't know that reality was probabilistic at its core. What might we discover tomorrow that overturns everything we think we know today? Intergalactic space is the largest, most unexplored environment in existence. It's almost certain that it contains surprises we haven't imagined, phenomena, structures, maybe even entities that our current science cannot predict or explain. The void might be hiding the biggest secrets of all. This is why I love thinking about intergalactic space. It's not just that it's big or empty or strange. It's that it represents the frontier of human knowledge. It's where our science becomes speculation, where our certainty dissolves into mystery, where we're forced to confront how much we still have to learn. Every generation thinks it's close to a complete understanding of nature, and every generation turns out to be wrong. There's no reason to think we're any different. The universe is far stranger than we know, and intergalactic space, in its vastness and emptiness, is a constant reminder of this truth. Coming up, our final chapter. We bring together everything we've learned, can ask, what does it all mean? What have we discovered about the space between galaxies? And what does it tell us about ourselves? We've reached the end of our journey. We started this exploration with a simple question: what exists between galaxies? And we've discovered that the answer is far more complex and fascinating than anyone could have imagined just a century ago. Let me summarize what we've learned. Intergalactic space is not empty. It contains the intergalactic medium, a sparse but vast ocean of gas that holds more matter than all the galaxies combined. This gas is heated to millions of degrees, ionized by the radiation of distant quasars, structured into filaments and walls that define the cosmic web. The cosmic web is the fundamental architecture of the universe. It consists of dense clusters connected by filaments, surrounded by vast empty voids. This structure emerged from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years. Dark matter shapes everything we see. It provides the invisible scaffolding on which the cosmic web is built. Without dark matter, galaxies and clusters would not exist in their current form. Yet we still don't know what dark matter actually is. Dark energy is driving the universe apart. It's causing the expansion of space to accelerate, slowly stretching the cosmic web, widening the voids, pushing distant galaxies beyond our cosmic horizon. The far future belongs to dark energy and to the emptiness it creates. Wanderers populate the void. Intergalactic stars, ejected from their home galaxies, drift through the darkness for billions of years. Rogue planets, untethered from any sun, float in eternal night. Perhaps even black holes prowl the intergalactic spaces, remnants of ancient galactic mergers. Radiation fills intergalactic space. The cosmic microwave background, the cosmic neutrino background, extragalactic light, cosmic rays, gravitational waves, all permeate the void, carrying information about cosmic history. Life might, conceivably, exist in intergalactic space. Planets orbiting intergalactic stars, organisms in the subsurface oceans of rogue planets, even exotic forms we haven't imagined. The possibilities are speculative, but not impossible. And the void has meaning, not inherent meaning, perhaps, but meaning we create through our observation, our wonder, our willingness to ask questions and seek answers. But beyond these facts, what have we really discovered? I think we've discovered something about ourselves. Humans are curious creatures. We're driven to explore, to understand, to push beyond the boundaries of the known. This drive has taken us from caves to cities, from Earth to the moon, from ignorance to knowledge. And now it takes us to the spaces between galaxies, the most remote, most inhospitable, most empty environments in existence. We will probably never visit intergalactic space. The distances are too vast, the journeys too long, the conditions too hostile. Even our most advanced technology cannot bridge the gulf between galaxies. We're almost certainly confined to the Milky Way for the duration of our existence as a species. But we can know intergalactic space. We can observe it with our telescopes, model it with our computers, imagine it with our minds. We can understand its nature, its history, its future. And in doing so, we extend ourselves across the cosmos. We become, in a sense, beings of the universe, not just creatures on a single planet, but conscious participants in the cosmic story. There's something beautiful about this. Here we are, tiny creatures on a small planet orbiting an ordinary star in an unremarkable galaxy. We've managed to comprehend the largest structures in existence. We've mapped the cosmic web. We've discovered dark matter and dark energy. We've understood, at least in outline, the architecture of infinity. This is what humans do. We reach beyond ourselves. We ask questions bigger than we are. We seek understanding, even when it doesn't serve any practical purpose, simply because understanding is what we're for. Intergalactic space challenges us to think bigger. It shows us a universe that doesn't care about us, doesn't need us, might not even notice if we vanished tomorrow. But it also shows us a universe of extraordinary beauty and complexity, a cosmos worth understanding, worth marveling at, worth existing in. I want to leave you with one final thought. The universe is almost entirely empty. The voids between galaxies make up most of space. If you measure the cosmos by volume, emptiness wins by a landslide. But if you measure the cosmos by significance, by complexity, by beauty, by meaning, then the rare pockets of matter might matter more than all the void combined. We exist in one of those rare pockets. We're part of the cosmic web's bright nodes, not its dark spaces. We're matter that has become aware, emptiness that has learned to see itself. And when we look out at the void between galaxies, at the darkness, the emptiness, the silence, we're not just observing something out there. We're confronting the mystery of existence itself. Why is there something rather than nothing? Why does the universe exist? Why do we exist? Science might never answer these questions. They might be beyond the reach of human understanding. But asking them, that's something only we can do. That's the unique gift of consciousness. The void doesn't ask questions. It simply is. But we small and fragile and temporary we ask. And in asking, we transform the cold equations of physics into meaning. That, perhaps, is the true significance of intergalactic space. It's the contrast that makes us visible. It's the emptiness that defines our fullness. It's the silence against which our music is heard. We are the universe becoming conscious of itself. And when we contemplate the spaces between galaxies, we're completing a cosmic circuit matter, reflecting on matter. Existence contemplating existence, something wrestling with nothing. Thank you for joining me on this journey. Thank you for sharing these hours of exploration. Thank you for caring about the universe we inhabit in all its vastness, all its strangeness, all its terrifying, magnificent emptiness. And there you have it. We've traveled together through one of the most fascinating and mysterious aspects of our cosmos, the vast, seemingly empty spaces between galaxies. And I hope you've come away with a new appreciation for what exists in the void. Let me give you a quick recap of what we've covered tonight. We learned that intergalactic space is not empty at all. The intergalactic medium contains more matter than all the stars in all the galaxies combined. It's just spread incredibly thin across unimaginable distances. We explored the cosmic web, the largest structure in the known universe, and saw how galaxies are, connected by filaments of matter, surrounding vast empty voids that make up most of the universe's volume. We confronted dark matter, the invisible substance that shapes the cosmic web and outweighs visible matter by a factor of 5 to 1. We still don't know what it is, but we know it's essential to the universe we observe. We discovered dark energy, the mysterious force driving the acceleration of cosmic expansion, slowly stretching the voids, pushing galaxies beyond our cosmic horizon, and ultimately determining the fate of the universe. We met the wanderers of intergalactic space stars, ejected from their galaxies, planets drifting without suns, black holes prowling the darkness. These objects, once thought impossible, turn out to be common. We trace the far future of the cosmos, the fading of stars, the evaporation of black holes, the heat death that awaits in the inconceivably distant future. And we grappled with the philosophical implications of it all. What it means that most of the universe is empty, whether life might exist in the void, and what significance we might find in the face of cosmic vastness. This has been a journey across scales almost impossible to comprehend, from individual atoms to structures spanning billions of light years. And we've only scratched the surface. There's so much more to learn, so many mysteries still unsolved, so many questions still unanswered. That's the wonder of science. It never ends. Every answer reveals new questions. Every discovery opens new doors. The universe is infinitely more complex than we can ever fully understand, and that's what makes exploring it so endlessly fascinating. Now, before we part ways, I have a request. If you've made it this far, you're clearly someone who cares about the deep questions. Someone who wants to understand the cosmos, not just skim its surface. You're exactly the kind of person I make these videos for. So here's what I'd like you to do. First, I'd love to hear your thoughts in the comments. What surprised you most about intergalactic space? What questions do you still have? What topics would you like me to explore in future videos? Your feedback helps me create content that matters to you, so please take a moment to share your perspective. Second, if you enjoyed this video, consider subscribing to the channel and hitting that notification bell. I create deep dive explorations of cosmic mysteries on a regular basis, and I don't want you to miss the next one. Third, liking and sharing this video helps more people discover it. YouTube's algorithm responds to engagement, and every like, every share, every comment helps spread the wonder of science to new audiences. And finally, if you want to support this channel even further, check out the Patreon link in the description. Your support helps me devote more time and resources to researching and creating these videos. I want to end with a thought that's been on my mind throughout this exploration. We live in an age of unprecedented cosmic knowledge. 100 years ago, we didn't even know that other galaxies existed. 50 years ago, we hadn't discovered the cosmic microwave background. 20 years ago, we didn't know about dark energy or the cosmic web. And now, here we are mapping the large-scale structure of the universe, detecting gravitational waves from merging black holes, peering back to the first moments after the Big Bang. This is a remarkable time to be alive. We're the first generation in history to have a scientific understanding of the cosmos that is fundamentally correct, at least in its broad outlines. Future generations will refine our knowledge, correct our errors, fill in our gaps, but they won't overturn the basic picture. We know, broadly speaking, what the universe is made of and how it came to be. And that includes the vast, mysterious, beautiful spaces between galaxies. Thank you again for watching. Thank you for being curious. Thank you for caring about the universe we share. Clear skies and keep looking up.